All right. Hey everyone. Um, I just switched my turn on my mic, so I'm making sure you can hear me. Yeah, welcome back. So last week we implemented a bunch of stuff. We got to the point where factorial was actually working and printing out the results as a number. Uh, and I later on also tried to write an example offline of sound is good, maybe a tiny bit quiet, but totally fine. I can try to raise the volume. Actually, maybe I'm just like farther from the mic. Is this better? I'm a little closer now. Um, okay, yeah. So what I was saying is, last week we got factorial to work, and then I later on just wrote a simple example of Fibonacci, and that was working fine too. And we can print numbers, so that's pretty good. This week I wanted to like get into some really useful features that will help us write the actual programs, like the actual compiler with this compiler. And so things like local variables, but mostly like pointer arithmetic and pointer management. So currently there is no way to take an address of a variable, for example, in our system, or dereference a pointer and then like store things or read things from it. We'll get to that. And I do realize that now the way we are handling expressions is also not great. So we currently can handle like one level of expression with a binary operator, or like maybe like a unary operator. But the problem is, when we have more than one, we're not really implementing precedence, which causes like those to associate wrong, or like yeah, the precedence is wrong, so you'll get wrong results. And the solution I had in my mind for this was you just require users to put parentheses everywhere. Um, it just doesn't work. I think that's a little too restrictive even for a language of this scale, because eventually we'll be writing big programs and we would want to be able to do like, hey, a plus b minus c, or something like that. And I think it should be handled properly. So we're going to implement some precedence today too. And then finally, I want to get to the point where we can actually produce an executable. So all this while we have been generating instructions and then just directly jumping to the instructions and executing them. I think it would be great to be able to also generate that as an executable. And then run the executable multiple times if you want, because that's how compilers work, right? You shouldn't have to compile every single time to run something. I mean, as our compiler gets bigger and as we write more programs, the bigger programs, the compilation is going to be slow too. So you don't want to have to pay that like cost every single time. Okay, so I'll just start sharing my screen. Okay, yeah, this is where we were last week. So one thing I did after I got off was I just went and added some comments. So I realized that I have been writing a lot of code, especially for the code generation part, which is a bunch of constants, right? Like if you look at basically stuff like this, it's not clear what this is. Like 50 E50 E589485. What is that constant? So what I've done is, screen looks great, perfect, thanks. What I've done is gone back and added comments to everything that is code generation. So for example, what this is showing here is this E58, whatever this number is, it came from these instructions, and those instructions are here. And this will help us with a couple of things. One is, if we want to change some instructions later, we can like quickly do some surgery on it without having to remember every single, like decompile every single constant or disassemble every constant and so on. Yeah, so I've done that for all the instructions. For major stuff like, actually this if condition has also been added here, so we can remove this big block, but I've kept it now for just for the big picture stuff. But yeah, every single instruction where code gets generated, I've added some comments. Hopefully for folks who are watching afterwards and reading through the code, this will also help. While I was doing this, I actually also found a bug in our implementation. So this was specifically in the last change we did for the this part. Read this shift and oh, what happened here? This shift. The shift part, I had made a mistake. So remember we had this bug earlier where we were shifting too early. So this check was here, meaning before we even read the next character, we were actually shifting like the value in the registers to the higher registers to make space for the new characters. But the problem with this was, if you are at the end of identifier, like say at a 8 letter identifier, which I think put char was the reason. What would happen is it would get shifted and then you would get a wrong identifier name. And to fix that, what we did is we moved this down so it only shifts if it actually needs to store that character. So if it is already ended, which will happen by either end of file, or it might happen by getting a space. And if either of those happen, we don't need to shift. The problem, however, was I jumped to shift and continue. And the way it was written previously was because this was at the top, because this was here, if we jump to shift and continue, it will actually fall through into the same code. But now it actually would skip a character. So what would happen here is we read a character, we realize that, hey, I need more space. I make this space, and then I just discard the character. I never stored it. So this actually needs to go back. Now, one way to handle this is put a jump here. But rather than that, let's actually do this the right way. So what we can say is if it's not 0, shift and continue. I'm going to change this to if it's 0, meaning there is space in our thing, then I'm going to simply say read till end continue, right? And then this can just go directly in line to make space, and this becomes read till end continue. So we don't need the shift and continue to be outside of this block. It's just like an inline jump now, and this should handle it. Yeah, just some cleanup from previous session, that a bug that I had found. Somehow it didn't trigger because we never had identifiers longer than 8 characters. In today's session, I'll try to write something that's longer, and hopefully that will work fine. Okay, so this is good. We now have like previous bugs cleaned up. I'm just going to quickly make sure everything runs, and let's try running the factorial example we had from previous. Yeah, and we get 120. To remind folks, the factorial program was this, where we were taking factorial of 5, which is 120. I also wrote a Fibonacci implementation. It's nothing fancy. It's the same. It just has 2 recursion instead of 1. So you have fib of x minus 1 or x minus 2. And this should also run correctly. Yeah, and we get Fibonacci of 6, which is 13. The way I had written this earlier, by the way, I wrote it a little differently. So you see how there's this 2 conditions, one after the other. Ideally, I wanted to write this, right? One, we currently don't have the OR operator implemented. That's part of it. But the second is, even if we implement that, we don't have write precedence, right? Because what will happen is x equals 0 would be passed, and then immediately the OR x would get passed into it because we don't have precedence, so it's just going to keep on feeding stuff from the right into the expression. And so we need to fix this. We'll fix this thing next, but first I'll handle local variables. Because if you remember how we did the factorial implementation, we had to do x equal, this is again problem because of not having precedence, but I had to basically update the argument itself. So instead of doing like a local variable equals to x colon %10, I had to write x equals x %10. It's not wrong, but it would be good to have access to local variables. Right now, the only way we can create local variables is by adding an argument. And it's not very difficult. Like adding local variables is just, we already have a local symbol table, which keeps track of what variables are alive in the function scope. All we need to do is just be able to create more declarations. So that's what we'll handle right now. Let's go back to the parser. And so we need to start with a statement. We need to start with the statement. But before we actually go to statement, we have this local stack slot or current function stack slot or something that we called it, right? Which was telling us current function slots. This keeps track of how many slots in the current functions have been used up. We will continue using this. The only thing is this needs to be reset now because we did the part about the functions arguments. We now need to go and reset it for the actual local variable. So we had this fixed local symbol table for args, by the way. We can just use that and and do it. So here, once we are done with reversing the values and offsetting the stack slots correctly, we just go and reset it. So I'm just simply going to do move $0 into current function slots of %RIP, right? So this will prepare it for the next one. However, I don't think this should be 0, it should be -8, right? Because the first argument is going to be at -8. So I'm going to set this to -8, and then as we go along, we'll just keep subtracting from it. I mean, I could start with 0 and then use the like a -8 of it, but it just easier if I start from -8. Okay, so this part is done. Now, when we go into the function parse function body, this is where we start parsing statements, right? So we go here and we parse a statement. We'll now have to allow statements of type declarations too. So what we'll simply do is we'll just add another case. So currently we have semicolon, which says it's an empty statement. There's nothing to do inside it. That's fine. We could have a return statement. We could have an if statement, a while statement. And next, what we're just simply going to say is this a type? Like if it starts with a type, then it must be like a variable declaration. Now, it's generally hard to know if something is a type because we might have identifiers later. We might have custom types later. I mean, currently what we can simply do is if it's one of the known types, like if it's either like integer, it's int or char or void or something like that, that would tell us that, hey, this is a type, which means we should go to parsing a variable declaration. But the problem is we don't actually have a way to know, given just an identifier, whether it's a type or not, because later we might add structs, right? So the simple way to do this is we actually make a function called isType, right? And if that says true, then we don't actually, I mean, it'll sort of like look at the tokens and tell us whether, hey, this is a type or not. So what we're going to do is we should return the token, and then let's just call isType. Or we could just have the first token in the RAX right now, and just, yeah, we could just like do check type or something like that. So let's just jump to actually let's do call check is type, right? So this is like parse type, but instead of instead of actually parsing the type, it just tells us that whether the current token that we have is a start of a type or not. Check is type. Actually, I'm also going to move it to a different location. So before a different register. So let's move it to, because we'll have to return the true or false in RAX. So this will allow us to use both of them. Okay, so let's now, the logic for this would be exactly similar to parse type. For now, we'll just compare if it's char, int, long, or void. Later, we'll have to add code to say, is this also one of the custom structs? And that will be an identifier, which will be one of the sort of like, we'll have a table corresponding to the current defined structs, and we'll check one of them. But for now, I'm just going to quickly check if it is actually. So let's start by setting RAX to 0. And then let's just check for one of the, if it's, doesn't that massive grad rats thing get in the, you can see it on my screen? That's surprising. So yeah, I do have my grad rat on. I've just gotten used to it now. Don't mean to use it as a flex. I don't even feel it these days. Like when I got it in the beginning, I used to take it off at night because it was heavy. But now I don't even realize it. So it's just there on my hand all the time. But yeah, thanks for asking. Okay, actually, so instead of returning from this, instead of returning like defaulting to 0, let's actually set it to 1. So right, and then yeah, so if it's a keyword, then we simply say jump on equal check is type return, right? And then check is type return just returns, right? And then the final case where it's not one of the types, we'll just set it to 0. So this is where we'll do x, rx. That way we don't have to write too many cases. Okay, so this goes here, it becomes if it's int, or if it's long, or if it's void. Yeah, I think this is all we'll allow for types. I mean, no matter what type of complex types we support later, it always has to start with one of these keywords, or it has to start with like a struct. I mean, honestly, C is easier to parse because it literally has to use the struct keyword. You can't really use a type directly. So in fact, in the future, we can just simply add here, just do this, and this will be fine. Which is eventually what we'll do. But for now, because we only support the basic types, we will keep it like this. And this is easy. So now we go back to check is type, which was here. Yeah. So now in RAX, we have the result. So we check. We say test Q RAX. I mean, we could also, actually, the flags must be set correctly already, but let's not rely on that because later we might change the logic. So let's test it again. And now we say if it's jump on equal, yeah, jump on not 0, sorry. Yeah, jump on not 0, parse variable decal, right? And if it's not, we should move it back. So %RSI goes into RAX, and then we can do return token. Yes. So by the way, return token is a special function. Normally, our functions take arguments in RSI and RDI, but this particular one takes an RAX because it sort of like is a undo of the get token, and because get token returns an RAX, RBX, it's just easier to do return token without having to move registers around. So return token sort of like takes the argument in RAX and RBX too. So yeah, that's a special case. Okay, so this is done. We have parse variable decal checked. So now we should go and implement that. So this was while if finish. Okay, let's add it here. Parse variable decal. So we already have the token in the. Let's look at some of the other statements. So right, so here we did get token for must be the parentheses, right? Yeah, so the first token of that statement has already been used. So what we should do is return that token, right? Because we're going to pass the type now. So we're going to say parse type. Now parse type requires everything back in the it needs to start from the start of the type. So parse type we have now, and usually we move parse type. There was a parse global, right? Parse global variable. Just mimic the logic of parse global variable. So we did this. So we took the type and we moved it. Oh, this was already done. Right, so we had the type in R12. No, we had the type in R11 and the identifier name in R12. Okay. Wait, what did I call it? Yeah, variable declaration. Okay, so we have move q percent RAX is the type, right? Yeah, so into R11, and then we will parse the identifier. So we say call get token. This must be an identifier. We should report an error. Compare RAX with token identifier. I think identifier is capital. Yeah, okay, so we have token identifier if jump on not equal parse variable decal error, which we will define here. Move Q into RSI. We'll move, we'll have to write some error messages first. So we'll call it parse variable decal error message. Variable declaration expected variable name. Why is everything capital? Okay. Sorry, these names are getting too long. Okay. So let's load the address of the message first into RSI and then move message len into RDI and then jump to report it. Okay, so now we have consumed the token, which is an identifier. Now we can move the RBX into R12. Okay, so we have the local, we have type in R11, and we have the name of the variable in R12. And at this point, we should, again, the logic goes back to if we have initialization or not, which we will add later, but for now, we will just consume the semicolon. What I'm going to do is make sure that it is semicolon because I keep forgetting things. No, not token identifier. Token, it's keyword semicolon. Token semicolon, okay. And we'll just jump to the same error. Jump on not equal parse variable decal error. Okay. Now, assuming everything is correct, we need to add this to the local symbol table and give it a stack slot. So if you look at our local symbol table, the structure of it is what part are we working on? Calling conventions? No, we are actually working on local variables. So I just added the simple code to start parsing local variable declarations, which is basically a type followed by an identifier. And we are then assigning it stack slots, so then we can refer to those variables later. Yeah. And yeah, I was just talking about what things we're going to do next. I do want to handle precedence, operator precedence today, because I was writing some code earlier with factorial, Fibonacci, and it was just annoying to have to like break things down into smaller expressions, which again we couldn't do because we didn't have local variables. So it's just better if you handle precedence properly. And it's actually a fun exercise in handling precedence because you have a specific order that you need to enforce. Anyway, so yeah, identifier, index, stack slot, offset, and type of variable. yeah, sorry, identifier index stack slot of certain type of variable. So yeah, we just go and update the symbol table. Is the so the symbol table must not be zeroed out, because we have just gone and fixed the symbol table, which we did fix local symbol table for args. This just we went and flipped all the values by doing this, right? We took the maximum value of the current stack slot, negated it, and went and added it to all the symbol tables. But the symbol table still must be correct. Like the symbol table end has not been updated. Okay, great. So we just keep on adding more stuff. Okay, so now we are ready to add the entry to the table. So we will first load local symbol table end into RAX, and we should put the entry. So first goes the identifier index, which is an R12. So %R12 goes into simply RAX, right? Then we do the second was the stack slot. So we need to grab a stack slot first. Let's do that. So it should be in current function slots, right? Current function slot. Yeah, current function slots. And then we can increment this. We need to subtract this and put it back. Okay, we'll do that afterwards. So we can move that here, RBX into 8 of RAX, and finally goes the type. So far we haven't touched the type, but eventually we will do that. So 16% RAX, and now we need to update both local symbol table and current function slots. So we do LEAQ local symbol table. What was it? LTES, local table entry size, yeah, of RAX into RAX, right? And then move it back in, store it back into the local symbol table end. And similarly, RBX also needs to be decremented by 8. The reason it's decremented is because stack grows downwards, so I mean towards smaller values. So progressively the new variables that we allocate, they will be lower addresses. RPX into RPX, and then we move that back into perfect. Now we have okay. So we have updated our we have created the entry for the variable, and I think that should be all. All we have to do is create this entry, and we are ready to return. So this will create the entry. We also need to make space on the stack for this variable. So we haven't done that. Like we just allocated a stack slot, but the stack needs to be allocated. So what we're going to do for this is, as we keep on allocating variables, this current function slots is going to keep on increasing, right? At the end of the function, we will know totally how many variables were used. So we'll use that value to insert a sub instruction at the beginning of the function. However, when we start generating code, we don't know where that entry is, where that current sort of instruction like how many total variables there are. So we'll insert a jump, sorry, we'll insert a subtraction, but it'll be an empty subtraction. We'll go and later patch that in. That's generally how we do it. So let's go to parse function, not call expression, parse function body, I think it is called. Yeah, parse function. Yeah, so in parse function, we did some setup, right? Like we did parse argument, and we did this. Yeah, this is the part where we did push RBP, we did move RSP into RBP. We now also have to make, what is this? Held a message for reasons for detection. No, just some spam. I'm gonna okay, let's do so what's the easiest? So we would have a negative number in our current Slack slot. We just need to add that negative number to RSP. The easiest way to do this is probably to use LEA, so that's what I'm going to do. I think I must have function set up somewhere, right? Function called dispatch stack frame setup. Yeah, okay. So what we'll do here is LEAQ 0x1234 of RSP into RSP. Actually, let's make this a negative number, negative 1234 into RSP. So this way we will know how to exactly encode it. Okay. Let's look at the stack frame setup. So yeah, we have these are the encoding bytes till here. Yeah, it's a 4-byte constant, so it'll be FF, I'm guessing. Let's ask Gemini. What is in 2's complement 32-bit? Just to make sure that what we are doing is correct. FF, and then you add 1, so FF, is that correct? Yep, that is correct. Okay, so this is all we need to do. This much. Okay, so stack frame setup. This is already there. Sorry. Okay. So this is a 4-byte instruction, right? 488D A424. Yeah, so this should be easy to handle. You just do a single right. Yeah, so this goes 24 A4 8D48 into 4 of R14. And this becomes 8. Okay, so what we've done is we have created the instruction. Actually, this should be 12 because we also need to leave space for the 4 bytes. Actually, let's make it 8 because we need to store this into some variable. So parse function was never made recursive. Yeah, okay, that's fine. So we'll just make a global variable where we'll keep the stack slot. The address of the point which needs to be patched again. So let's move R14 into current function stack setup patch. Oh god, this is just getting longer and longer. And then we can do 4 of R14 into R14. current function slots. Current function stack setup patch. And it's just an address, so you just need 8 bytes for it. Okay, perfect. So this needs to be patched at the end of it. So that should happen here. Get function body cleanup. Sorry, no, not get function body cleanup. This should happen at the end of the function, like completion, not because this get gen function body cleanup also gets called when there's a like an intermediate return statement in the middle of the function. That shouldn't patch this address. This should only happen here. Yeah, so after we're done generating body cleanup, we just need to go and patch that function, that address. So we simply do current function slots of RIP into RAX, and then we move RAX into we need to load that address first. So current function stack setup patch of RIP into RPX, and this is actually, so we have been keeping around this value as a 8-byte integer. However, the instruction only needs 4 bytes. Now the good thing about negative numbers or even positive numbers is you can just truncate the higher bits and it is the same number. So you don't actually have to do sign extension when you're going down. You just have to do sign extension when you're going up. For going down, it's just truncation. So we will simply do move L here, and we will use EAX. So that way, yeah. And then this gets stored into RBX. And that's it. We have our stack setup done, and if everything is done correctly, our reference to the local variable should also work properly. So we're going to test this. First, let's compile it. Okay, there is some issue. 431. What? Expecting append after. Oh. 446. Unsupported syntax for jump for 454. Okay, now let's write a simple example. Local var.c. So let's do it directly in main, which is easy. Actually, we should do it not in main because we want to make sure that it works correctly with arguments too. So int foo int x comma int y, and now let's declare a variable. So we'll say int z. Currently we don't allow initialization, but we can do z equals x times y, and then we can do return z, right? Yeah. And in this we can simply do return foo of 3, 5, should be 15, right? Okay. This is bad. It's got stuck into an infinite loop, which is, this has never happened, but we can check. Report error loop, huh? Oh, report error loop should print something. Why did not print? Did I set the message length wrong? Variable. Oh, no, this is correct. Parse variable tackle error message len. Did I use argument order wrong? Just in driver, right? Report error expects RSI RDI. That is correct. Let's look look at some other report error. Here it is. We have invalid expr into RDI. Oh, okay, I guess I remember it wrong. Okay, variable declaration expected variable name. So something went wrong. Let's look at our code first. So we have int z semicolon. This is correct. So we call return token. Oh, we never call parse type. That should do it. Parser expected type. Oh, I know what's happening. The token is not in RAX, right? When parse variable is called. Yeah, RAX contains 0. Okay, so okay, better than not compiling. So code gen buffer. So it's crashing somewhere inside the executed program. Let's just look at the assembly for this function. Crashed on ret probably. Yeah. We can just step through this and see what happens. So break execute program, run, next I. First one is not correct, second one is correct. Okay, so now we jump to this, step into it. This is main, right? Okay, so main doesn't have any local variables, so it doesn't do anything. RSP is fine. This moves the address. Arguments 3, argument 5. Pop RAX, this is fine. What is this for? Oh, this is bringing the address into RAX. Then we call. Let's go step inside. Oh, okay. Okay, so this one is doing push RBP. Okay, this is correct. So we see now have -8 of RSP being generated. I think that should be correct, right? So we do push RBP. We have move RSP into RBP. So that holds our frame base, right? Base pointer, and then we have -8 of RSP into RSP. This should be correct. Oh, 0 of RBP into RAX. So this is interesting. Why is it doing 0? It should be -8, right? Because it somehow loaded the address of the return value into like the variable. Okay, let's see how the variables are referenced. Maybe we add 8 or something there, which might be causing issues. So check local symbol. Check local table. Yeah, here. Yeah, this just directly takes the entry, tells us where the entry is. Okay, so this is fine. Let's see the call for this. Here. Parse identifier expression local. Parse identifier expr local. Wait. If the constant is -8, means we did not create enough space. Yeah. Okay, there is. I think this is not the problem. The problem is when we set current slots, current function slots. Yeah. Starts with 0, goes to negative, and then we call fix for argument. I think this is where it went wrong. Yeah. Did this not happen? -8 of current function slot. So It should start from -8, and when we assign a function slot, it should go to -16, but we only have -8 created on the slot. So parse variable decal. Yeah, we should put a breakpoint on this and see what happens, because this is getting a wrong value. Okay. Parse variable decal. This can be fine. Parse type has been parsed. $x is, this looks like int, so that's correct. This is parsing identifier, so you can go ahead. Wait, why is the call name not being, function name not being shown properly in GDB? Oh, I guess. This should be fine. Okay, so this should also be okay. This is just parsing the semicolon. Okay, this is the one where we load into the number of stack slots. This is where we should check RBX. It is 0. Huh. How is it 0? Didn't we store minus? Didn't we store -16? -8 in that? Yeah, it loads current function slots of RIP into RBX, and this somehow is still 0. And we do have function arguments, so it must go into fix local symbol table for args. Okay, well, I guess we just put a breakpoint on this and check what happens. Okay. Seems fine. Why did it go to local symbol? Oh, this is the second function. It went to main. Why? This is GDB issues again. I have to step through this. Okay. This is 0 again, but we stored -8. Let's put a watch point on this and see what happens. Where does it change from? Oh, of course. Current function slots. Okay, let's start from the beginning. Couldn't write debug register, invalid argument. I think it should be address of. Okay. Okay, this seems correct. Let's start from the beginning. Okay, in parse argument, it just stored something. That's fine. Oh yeah, so old value was 0, now it becomes -8. This is correct. Then it became -16, then correct. And then it again got set to -8, correct. It became 0 again. Why? Because it goes to parse function body. Did we set it again to see? Yeah, I made a mistake. Parse function body. Here, for some reason, we set it to 0. Okay, this was causing the issue. So let's just also remove it from there, because I don't actually know if it gets called. If I don't remember if it gets called. Okay, so this should fix it. Okay, 15, perfect. We have some local variable at least working correctly. So this is good. We should test this in our Fibonacci. So instead of using x equals to x modulo 10, I'm going to say int y. Then I'm going to say y equals to x modulo 10. And then we can do y plus 78 here, 48 here. Let's check this. This is factorial of Fibonacci. Okay, we do have this working correctly. So this is good. Now we should just also support like this. All right. Right now, that is, oh, this is Fibonacci. I changed, my bad. It's like, how is that working? Okay, let's check this first. And that's wrong, because we did wrong. Okay, this is correct. And now we should get this to work. Okay. So now the annoying part is this can be an entire expression. It might be like a runtime expression. It doesn't have to be a local, like it doesn't have to be a constant, right? It's not like a global variable where it can only be a constant. So what we're going to do is we're going to just say parse expression if we see a equals. Yeah, so we expected semicolon here. So this is a little tricky. We need to allocate the stack slot first and then check whether, yeah, so we do this, we completely allocate the stack slot first, the variable is ready to be used, and then we get token, we compare it equals to, compare token equals, right? If it is token equals, then we jump to jump on not equal variable decal no init, right? And so this goes here, variable decal no init, and now here we can just parse the expression. So we say calls parse expr. Yeah, so token equals has been consumed. Now we do parse expr, and we need to generate code to store that value into the variable. So here RBX has this slot. The RBX has this slot, right? We should probably store it. Yeah, so I'm gonna do push q RBX. The RBX has already been decremented, so okay. So we'll call parse expression, and now we can do Okay, so we just need to generate code to store the value into the just allocated stack slots. So let's do that in here. So we just do popqrax, popqrax. So this gives us the value, and then we do move qrax into some constant. So 0x123 of rbp. Yeah, this is correct. Okay. It'll be a negative number, but that's okay. Right, so let's do this now. Move, what is it? Move W 0x58, 58. Actually, it's 1, 2, 3, 4. Yeah, this is going to be annoying. Let's just do 2 by 2. Move L 0x00858948 into 2 of %r14. It's just 5. And then we just have to store the constant, which we have in RBX. So we just do move L %EBX into %R14. Actually, let's just change this. Let's make this 5 and then make this 9. Okay, so now we have the constant computed and stored, the expression computed and stored, and this now should still consume the semicolon. Yeah, after equals there should still be a semicolon, which, yeah, token semicolon will handle. Oh, but we need to get that token. Glad you chose get to have your voice in my headphone. Thanks. I did not realize my voice was soothing to people, but thanks for attending, dude. And of course, the recording will be on YouTube afterwards. So you can watch it there later. Okay, we just need to call get token again, so the semicolon is consumed, and then we can compare that. This is perfect. Okay, let's test this out. It compiles, and then, yeah, we wrote factorial with a sign, right? So this should work correctly now. Nope. Variable declaration expected name. Let's save this. Okay, we'll have to step through this. Oh, it's not token equals, it's token assign. I keep doing this wrong. Okay, segmentation for code dumped, but that's okay. We probably messed up return address again, so we just debug this. We should actually just check this in a smaller function instead of doing this for the big one. It's going to be hard to step through the whole function. Let's do local var here. I hope this crashes too, so we can test this. It does crash. Great. completely get screwed up. Okay. Okay, in quotient buffer now. So this is main. Main doesn't have any local variables, so we just allocate one stack slot. This can probably be fixed later, but that's okay. This is local variable, and this one has one stack slot allocated. That's correct. First argument, second argument. God, this is so slow. This is the actual. Oh wait. Yeah, fine. Nothing has to be generated for the variable creation, so this is fine. This is all good. Multiplication. This is fine. Okay, so this is wrong. It moves RAX into 45 RBP. That's obviously wrong. So we need to change this. 45 RBP. Okay. Oh, because we call get token here. Let's change the RBX value. What should I store it in? Problem is if I push it here, pop it here. Okay. This way it's always correct. Okay. Nope, still wrong. Push QRBX, pop QRBX, token assign. Okay, this time it should be correct. Yeah, this seems good. Okay, I'm going to make it. This is the first main function, so this is fine. It's 3B RBP, so it's still wrong. What is 3B? Yeah, it's semicolon. Somehow this semicolon is being inserted as the stack offset. Oh, call parse expression changes that. God, this is so annoying. I should just make this into something that has a stack frame. Yeah, you know what? I'm going to do that. This is just too annoying. 8 of RPP is for variable slot. Okay, instead of just trying to keep it in register and making space for it, we'll just allocate it on the stack and then keep it there. Just better way to do it. Okay, this ran correctly. 15, perfect. Let's also check if Fibonacci and factorial work now. That does work. And Fibonacci also works correctly. Okay, great. So we have local variables working. We have local variable initialization also working correctly. Let's do operator precedence next. I'm going to quickly save this. Added support for local variables. Okay, great. This is good. Now let's add support for operators. So operator precedence. So let's look at how C operator precedence works first. Currently we are handling binary operators. That's what we'll focus on right now, but eventually we'll scale it up to everything. So there's several hierarchy of operators, right? Like at the very bottom we have the assignment and family of operators. Out of this we are only supporting assignment, so we don't need to support all of these, but we still have to support assignment, right? The comma is at the very bottom. We're not supporting comma, but you'll see that from this onwards, the binary operators, except for ternary, which we will skip for now, we have all these binary operators all the way up to 3, and then we have unary operators on top of it, and then finally at the very top we have the increment and decrement and square bracket and function call kind of operators. Also, there should be parentheses somewhere. There isn't parentheses. I guess parentheses has highest precedence by definition, which is like if you have an expression inside parentheses. So what we're going to do is we will make a recursive function that can parse every higher order of precedence. So I'll give an example of this and how this works. Let's go to .io. Oh, this is our previous one. Imagine we have an expression like this. You have A times B plus C, right? Now, there's two different precedence being, actually, let's make it even a little more complicated. So let's say we start with D plus A star B plus C, right? There's two different precedences playing here. There is precedence 4, which is for addition subtraction. There's multiplication for 3. So we need to somehow if I pass this right now, it's going to give us wrong code. So let's actually make a test case for this first. src precedence.c. I'm going to get integer. I wish I had a way to do include, so I don't have to write this every single time, but I guess at some point we'll add that as a feature. Okay, so and since we have local variables, now we can use them. So int x equals to ABCD, right? A equals 5, int b equals 10, int c equals 4, int d equals 9, right? And then I'm going to say put integer of d plus a times b, let's say minus c, just to give everything an option. And then put char of 10. This is new line. Okay, and then return 0. Let's test and see what is the expected result first. So we have 9 plus 8 times b is 50, so it's 59 minus 4, so it should be 55. No. Yeah, 9 plus, God, this is hard. 55, yeah. What do we get? Where did I save precedence? Oh, in source. So we get 39, which is wrong because the parsing order is wrong, right? So we parsed this wrong. So how should this be handled? When we start parsing, we need to parse d first because that's the very first expression, and then we see a plus. Now plus is at operator precedence 4. So we say, okay, we're parsing operator level 4 now, and then we see a. We immediately cannot create d plus a because the a might not be a complete expression. We have to check if anything of higher precedence is happening first, and if it does, we need to keep doing that. So we say, okay, actually let's hold on, let's not merge a into the expression first, let's keep checking next. So you say, okay, we see a star, which is higher precedence than what we currently were at, so we keep consuming that. We see, okay, a star b, and then we see a minus, which is the same precedence as what we previously were at. So then we go and merge that a star b into the previous expression and then continue. So this is like, we're basically constantly going up and down the precedence as we're parsing. Like for example, if there was also like say a shift or a equals in the mix, right? It would have to go through 3 different precedence level. So we actually are going to write a simple algorithm for this. And let's see if this makes sense. So we say parse expression. We're actually going to take like I'm writing it like this. Yeah, I'm going to take as argument the precedence level, the current precedence level, right? Let's call it pre. Okay, and what we're going to do is for each precedence level, we are going to like try to consider the expression with this precedence level. But before we do that, we're going to like call parse expression of higher precedence level. So you're going to say, can we actually parse this expression as something of the higher precedence, right? At the very top of this, like at the very top of all the precedence, we will have identifiers. Like at the very 0 precedence is identifiers. If we see a variable name, that is the highest precedence, right? So what will happen is we'll start from the lowest precedence. We'll start from 15, or in this case, I should just start from 12, because actually 14, because that's our lowest precedence we support. So let's call this actually parse expression with precedence, and then we'll have a simple parse a general parse expr which doesn't take any precedence, and this will simply call parse expr precedence with 14. So we'll start parsing. I wrote so much of this C that I can't write normal C now with like reasonable. This is going to be a problem. I have to revert back from this. Okay, so what we're doing is we're starting from parsing 14, and what this will eventually do is we'll first recursively call at a lower level. This will eventually reach level 1. So where we say if precedence equals 0, which is at the top level, then we parse identifier expression, right? Because at this point, the only thing that can happen is it can be like a literal expression, like a identifier, right? We're actually going to cut it short at 3 because we haven't supported these operators yet. So we will simply like at precedence level 2, we will jump to parsing an identifier. So this will recursively keep on going from 14, 13, and so on. But once we have done that, we have to check if there is anything of this precedence available. So we say if next token dot precedence equals pre. So we'll have to implement some mechanism of like checking for binary operators and checking what their current precedence is. And if it is of this current one, then we also do parse expression of pre minus 1 because it's a binary operator, right? And we keep on doing this till we see the same thing. So we say while 1, do this, else we break. And this constructs the whole expression. Now, when we start parsing our expression of like d minus b plus a times b minus c, what will happen is we'll start with precedence 14. There's nothing at 14 because there's no assignment. Actually, we don't need to handle assignment because we're handling assignment separately. We're not handling assignment as part of parse expression. If I remember correctly, I'll check. If you're handling it as part of assign expression, then we'll have to do it correctly. But yeah, so what will happen is we'll try to parse this d. So we'll keep on recursively going through this whole height. At some point, we'll reach plus, which is precedence 4. We'll try to call precedence 3. Then it will eventually call expression. The next token is not of 3, right? The next token is plus. So this will not enter. This will immediately break and it will return. Now we reach A, which will again go up to higher precedence, reach parse identifier, nothing happens, it will come back. And now it will see star. But before going back to the 2 level, it will immediately just like consume this star, generate code for, this should be parse expression and then generate code for token. Generate code for token. Whatever this is, so t equals this for token t, and then this should return, let's make this correct, so get next token and then else return token t, right? Yeah, again, this is pseudocode, this is not accurate, but yeah, so what this will do is handle the times b, right? The plus hasn't been generated yet. We haven't done that yet. And then it will return out of the star because when it goes back again, it says it's minus. This is not my precedence. I'm going to return and go back again. And then when it returns from this sort of A star B, it will then generate code for the plus from the previous one, go back to the loop again, generate C, and handle it. So basically, it's like creating this recursive way of parsing expressions with different precedence. Fortunately, we don't have to handle associativity because all associativity of these binary operators are left to right. So the only like associative issues are with these expression and assign specifically. So if we do have assignments, they need to associate from right to left. So we'll have to handle that separately. But generally, all binary operators are left to right. So that logic just works. And that's the easiest way to handle this. So with plus, what we'll have to do is we'll have to keep going to the right till we see plus, and basically this would have to like this generate code would have to go somewhere here. Like we'll have to unwind from that while loop and keep generating the parse expression for the right to left associativity. But we'll handle that next. We'll first start with this. So Let's go to our parse expression. We had supported integer, identifier, and that's it. But where was assign done? Oh, it was part of binary operator itself. So you're checking for all binary operators, and we were checking separately for assign. So this is fine. We can special case assign, or we can put assign in the binary operator table too. Let me think about it. Do we want to put assignment in the binary operator? It's nothing. It is special in that it does an L value assignment, not an R value assignment. So that's going to require a slightly different code generation. Yeah. Let's handle assign separately. So the first thing we need to do is to put these precedents into the table. So here we have the binary operator table, right, which gives us information about all these operators. We'll have to change this to also add information about the precedence. So 8-byte for operator. It's not. This is 8 now. What is BT? BTS is 16, right? We'll have to change it to 20 because 20 or 24, right? Okay, so now for each of the structure, you're going to say 8 bytes for operator, 8 bytes for precedence, 8 bytes for instruction, including push. Okay, so let's just put the values here. So token plus is 4. Token minus is also 4. Token star is 3. Token divide is 3. Token percent is also 3. Equals is equals equals, right? So that's 7. Not equals is the same as equal, so that's also 7. Less than is 6. Greater than is also 6. Less equals is also 6, I'm guessing. Yeah, they're all the same. Greater than equals is also 6. We will eventually add the bitwise operators, which will go into the same table. But now basically we have the information about all the binary operators. We just need to make sure that first we don't reference them wrong. So this is just comparison, check next binary operator. Oh, here RCX is what contain, right? Yeah, the entry is in RCX. Right, so where was the part? Yeah, here's the part where we actually write 8, so this becomes 16 because we have precedence in the middle. Okay, but this part is going to change. Like, it's not going to look exactly the same anymore. So let's go to parse expression. Okay, so parse expression will directly call parse exper pre, and we'll have to move different precedence into it. Actually, no, parse exper assign. Like, you have to first check if it's precedence 14, which needs a special handling. So now it does say parse exper assign as in like the assignment expression, but actually let's use a clearer name, parse exper 14. So this 14 is a special case. We don't actually mean that literally, like, we don't want to make a separate function for each precedence level. We're going to just use an argument. But for the parse expression, it's simply this. where was the return value from parse expr? Yeah, here, parse expr end, right? Yeah, the semicolon needs to be consumed. So let's think about this. Actually, we can go. I'm thinking about where the semicolon gets consumed. I think expert doesn't consume semicolon. Um, this return token shouldn't be here because whatever sub expression is consuming it will return it. So actually we can just do return here then. Okay. We need to start by writing parse expr pre-14. So parse expr pre-14 is a special case, which is, I should put a comment. Special case for parse expr pre, which checks for assignment. Okay, so this will first call like precedence. Let's start from, I mean, we could start from 14, or let's just for now, sorry, not 14. We should just directly jump to 7 is the lowest one we support. So right, so we move it into RSI and then we say call parse expr pre 14. No, not pre, just pre. So this will parse it for the higher precedence, and then we will check if it's assigned, if there's an assignment. Now we do get token compare q, yeah, assign token assign token assign. If it is assign, then we do so jump on not equal parse expr pre 14 end, right? Parse expr pre 14 end just returns. Yeah, so this is basically the breakout of the loop. So here we'll check if it is, no, we need to return the token too. Yeah, we can't just return like that. If it's not assigned, we can call return. I mean, yeah, there's always going to be one token to be returned at the end, right? No matter what path we take. If it is an assign, then we call parse expr pre and then move $7 again, right? And then this will generate the second expression, and then we can actually generate code for assignment here. So where's that? What was this RCX for? Didn't need it. Right, so this so parse assign expression, we just generate the code for assignment expression. So this can just be copied. Okay, so this will generate the code for the thing, and then we just go back to parse expr pre14 next, which is here. Parse expr pre14 next. So this is actually wrong. This is still implementing left to right associativity. We'll have to change this for assignment differently, but for now we'll just yeah, this is wrong. We'll just put a to do here. To change associativity R to L. Right, currently it's left to right, so it'll do the assignment and then try to assign to that. So that's not going to be right, but yeah, this is fine. Okay. This is good. And now we actually implement the parse expr pre. This one takes precedence as an argument. So this one is easy now, but for this we'll have to actually use a stack frame because this is a proper recursive function. So push RBP, move parse into RBP, sub q, 8 should be fine. Wait, what is the order of arguments? Did I just make everything wrong? RSI RDI, yeah. Okay, move RSI into minus 8 RBP. Okay, so now we can go to the higher precedence. So we say decrement. Actually, no, we should check if we are at the top level first. Yeah, we should check if it's at 2. So compare RSI with $2. Jump on equal parse expert identifier. Do we already have that parse expert? Yeah. But this needs a better name. Actually, we can say jump on not equal parse expert pre continue, right? And this will handle integer expressions or identifiers. So yeah, this can go here. So before we handle, if it is precedence 2, which means we have reached the top of it, now it can either only be an integer or it can be a identifier. Yeah, so we check, we get the token and we check if it's an integer. If it's integer, we go to parse integer expression. If it's identifier, go to parse identifier expression. Let's check what it is. So parse. This is rewriting a lot of the code. So this one just passes the instruction and goes back to jump parse expr continue. Parse identifier expression also goes to parse expression continue. Let's go to parse expr continue. Yeah, so this one, right, so this one is not required anymore. Parse, we'll have to change this. Gonna give it some old label. So yeah, so if it's one of the integers are identified, there's nothing more to check. There's no operators, there's nothing, so this will just like immediately return uh, without consuming tokens or anything like that. So if you see if it's at level 2, it can either be an integer or it can be an identifier. Whichever it is, we parse that and we leave. So this is done. If it, however, happens to be a 2 or 3 kind of a thing, then we parse at higher precedence first. So we do decrement RSI, which actually we cannot. We'll have to load it first. So move Q -8 of RBP into RSI, which is our like current precedence. Now we actually decrement it, so we are at a lower precedence, and then we call parse x per pre, right? So this will recursively call itself, which means we can now, this part is done, and now we write the while loop. Now we check if the operator that's coming afterward matches our precedence. So the expression has been consumed. Now we say get token, and now we have to check if it's one of the binary operators of our precedence. So check binary operator. Yeah, here. So we have we should also store this token somewhere so we can return it if it's not correct before we start calling functions willy-nilly. So we need more stack slots. -16 24 of RBP is saved tokens. So we do get token, move RAX into -16 of RBP, RBX into -24 of percent. Remember, our tokens are two values. If it's an identifier or integer, it needs to be stored separately. Okay, so we have stable tokens. Now we say check binary operator. We check if the current token is a binary operator, which we can do here. So we load the binary operator table, we decrement it, increment it. We check if it's end of table. If it's end of table, we okay, so this is not required anymore. Oh, function call. So function call is precedence 1. Annoying part about function call is it needs to be handled as a unary operator. I think it can be handled with our like precedence 2. Right? So to clarify, these are like left. These are unary operators which appear on the left. These are unary operators that appear on the right. So what we can simply do is, as part of our integer or the thing, we can just keep on consuming these if we see them. So like once we pass the integer or the identifier, we just keep on looping and checking if we see any unary operators afterwards. So we'll handle that later. This can go away for now. This also goes away. Parse expression end can also go away. Okay, so we have check next binary operator, and what does it return? So we're to check if it's one of the operators first. No, we can clear. So this should return it in something. A token is in RAX, so we move it to just cleaning up some stuff that should have been written in a proper way. Okay, if we see a 0, then we go to n, which just clears RAX and says it's not found. Right? So returning 0 basically means it's not found. If it's not 0, then we compare RAX with RBX. If it's equal, then we just return. So we can say jump on not equal, check next binary operator, otherwise just return. Right? So what this is doing is checking which operator matches, and if none of them matches, it returns null pointer. And if one of them does match, it returns the address of that entry, which is what we wanted. Okay, perfect. So expr pre-continue, we first check if it's null. So we say compare $0 with RAX. Jump on equal, parse expr pre-finish. Right, there's no more expressions to parse. Parse expr pre-finish. Just like the assignment, it should return the token and then return. Right. But it should first load the token. So whatever last token we had consumed, just put it back. And then return. Okay. And now let's check it. Like, let's now, okay, so it's not, if it's empty, which means it's not a binary operator, we can return. If it is not empty, we have to check for precedence. So we say move q 8 of RAX, which is into RBX, compare q move q minus 8 RPP into RCX, compare q rbx rcx, jump on not equal, parse expr pre-finish, right? So if the precedence value doesn't match, which is here, if it doesn't match, then we return the token and break. If it does match, we need to parse the second expression. So this is getting interesting. And then if it does match, we decrement move q r. Just load this into RSI. Call parse expr pre, right? So if it does match our precedence, we go and parse another expression out of it with a higher precedence. And once that is done, we generate code for this binary operator. So we also need to now store RAX, which is current symbol minus 32 of RBP is current operator entry. So minus 32 RBP, right? So we have stored the current entry into RBP, and now we can actually generate code for it. So we have generated both the expressions. Now we say move q minus 32 of RAX into RBP. Sorry, no, RBP into RAX. And now we had the binary operator code somewhere, right? Yeah, this one. So we just actually need this code. Here, so just moves. Now instead of just RCX, it will be RAX here, right? Because we need to load it from, yeah, we have it in RAX, and this seems correct. Okay, so now our binary operator is generated, and we can jump to parse expr pre next. This is our while loop, which goes to here. Expr pre next. And eventually we'll see something that's wrong. I will jump here, we'll return the token and leave. Okay. So we, however, also need to, yeah, I mean, start from 14, eventually not, yeah, it'll just return back to parse expression. No, it'll return back to parse assign expression. This R14 is a special case. And that will eventually return here. So then we go to parse expr, which will also just return. Okay, so this should technically work. The function calls aren't handled yet. We will handle them later, but let's check our simple like precedence. So for now, what I'm going to, I can't do integer, that's fine. We'll just, this whole business is not going to compile. So let's remove this and let's simply do d plus a times b minus c, right? This was our expression. This should compile and run correctly. So and we got 55. So 55 is what we expected, right? 55 is, this is surprisingly like correct in the very first go. So addition, subtraction, everything got handled correctly. Let's actually make it a little more interesting. So let's say plus 16 divided by 2, right? So we are adding 8 to it, so 63. Oh, okay, so great, we have our first error now. So when it tried to parse 16, that was integer, and it says invalid identifier. Okay, so we have to handle that case. Here. Yeah, so in parse expr pre, we have this one, token integer. So this should be fine. We got invalid identifier. I think what's happening is did a bad fall through. Invalid identifier. It's happening here. Parse identifier expression. This is the only place where it's referred. Okay, so it went to parse identifier expression and then it couldn't find the identifier. Did I name the variables wrong? No. So 16. It's surprising because it worked correctly here. Like these expressions got parsed correctly. For some reason, when it got here, it went wrong. That's okay. We'll fix this. Parse expr continue. This should only happen at 2. Yeah, this seems correct to me. Why is this wrong? We might have forgotten to return a token somewhere, or pushed in the back the wrong token. Okay, let's check. Of course, we don't have any stack information because we never stored it. We'll have to jump to this. Okay, let's try to make a simple reproducible example so we don't have to. Does this fail? It does fail. Okay, so this is good. We can make a minimal example. This will be easier to parse. Does fail. So now we can do break parse expression. Okay. So this must be the first time it's called, which must be in the constant. This is fine. We can skip this. Continue. This is the second time it's called. This is where the actual expression is being called. Okay, so now we do next I. Actually, no. Step inside this. Now this is going to check if, no, this is going to first try to parse the highest level. So we go up, parse expression pre. So we have, there's no return here anymore. There's no assignment. So just simply go up. Okay. So this goes up. What is RSI here? Must be 7, right? Yep. Okay. Oh. Oh, it wasn't 2, which is the, yeah. Decrement. This must be 6, 5, 4, 3, 2. This time it must be 2, right? It is 2. Okay. Step inside. This time it's 2. So now we don't go here. Okay. And now we consume a token. So this must be A, which is identifier. Let's check the name of the identifier. 2. Sure. I'm guessing it's 2 is the index. Okay. Yeah, main is 1 and then this must, no, main is 0, put char is 1 and this must be 2. This is fine. Okay. Now we do next I. It's not an integer because it's identifier. So this goes on. This goes in. Okay. Parse identifier expression. This should be fine. This should be fine. It's not null, so this is good. Yeah, so it keeps doing this, and then it finally goes to parse expression continue, which just leaves and returns. This is correct. Okay. Now we are in the outer call. Yeah, okay. So we got the next token. What is that next token? It must be addition, right? To B. It's addition. Perfect. So we now have the addition token, but we are at precedence 3, which is not going to work. So we go here. It's not empty, but it doesn't match. So we go to finish, which stores the token back. Let's make sure we stored the right token. It is to be. Store the token, leave. Okay. Now this one calls get token again, so gets the same token. Now checks for binary operator. This will find it, but we should probably just store that information. That's fine. Looking up every single time, but that's okay. Parse expression pre-finish. Huh, wait, how did it get to? The binary operator matched. What precedence are we at? We're at 3, and 3 is star. That seems wrong. Oh no, we were at 4. Right, we were at 4 somehow. Okay, yeah, because after decrementing it's 3, so it must. Wait, we just did decrement RSI, which is fine. Yeah, it's the current precedence. Compare it, and if this matches, go. Yeah, this is fine. Okay. Parse expression pre. This is going to try to parse the multiplication. Okay, so let's go inside this. Yeah, this is where the problem is because we did 16 divided by 2, right? Yeah, okay. Let's make sure that we have the right precedence here. It is 3, so this is correct. Keep going. It's not 2, so this should go directly here. Perfect. But this will eventually call 2. Okay, this time it's calling it. This time it's 2. So it will jump to, this is good. Now we should, this should be an integer, right? It is an integer. Yes, that is correct. So we do next I, integer expression, tuck, 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 tuck. Expression continue. This leaves and returns. So now we are back to the plus, right? Yes. So we do next I. Oh wait, what is the token next? It should be division. 2f. Yeah, I think this is correct. It's correct. Okay. So this must have retrieved the division expression. We go next. It's not 0. Does it match our precedence? I think it does, right? Let's check. That makes us 3. Is also 3. So this is great. Which means now this will again try to parse at a higher precedence, correct? And this is I think where it errors. So we had precedence 2 again, which it goes inside. We parse an integer again. This should be, it is an integer. Jump here. Go back to parse continue. Return. Parse expression pre next. So we're done with all the things. This should generate code for multiplication first, right? Right, this is multiplication code generated. And now we go back to this. Okay, and then we get a token. It should be semicolon, right? 7D. It is curly braces. Where did the semicolon go? Okay, this was the issue. Where did the semicolon go? Where did my semicolon go? I did put a semicolon in the code, right? Oh, of course I didn't put a semicolon. Ah. This was as simple as this. Jeez. Yeah, this was correct. I'm an idiot. Plus 16 divided by 2 semicolon. Jeez. Okay, 63. This is what we expected. It was all correct. I just forgot to put the space between that and semicolon. Okay, lot of time wasted, but this is fine. Okay, so now we have our sort of precedence working correctly, but we won't have function calls working correctly. So let's check that first. Let's say function. Do we have a function call? Yeah. What is call? Bar 1 is 2 times 7 times 5 is 7 minus 5, so 2, so it should be 4, but we got 85, so this is wrong. Okay, function calls are not working correctly, which means we need to handle that first. So let's actually clean up some stuff that we don't need. So this check binary operator is fine, integer is fine, expression local is fine, identifier is fine, bias binary operator, expression. I don't think we are using this anymore. Anywhere, are we? Nope, so this can all go away. Are we using parse assign expression? Nope, so this can also go away. Parse function call expression we will use. Okay, so the way this will simply work is after we have done parsing integer, or it's like what, parse expr continue, right? Yeah, we've parsed integer, we have parsed identifier, whatever it is. We just need to check now if it is there's a function call here. So now we do call get token, compare L parent token L parent comma RAX, jump on not equal parse expr pre end. Yep, which is parse expr pre end. And if it, and this needs to just put in the token, return the token back. So call key return token. Perfect. If it is not a left parenthesis, then we go to the end by return the token. And if it is a thing, we just do jump to parse function call expression. Let's check that. Parse function call expression. So this does what it does and then returns back to parse expression continue, which is, yeah, so we'll just keep on checking if there is basically more function calls, because a function call can also return a function, which means it's basically all the these operators will be checked here. So we'll check for plus plus, we'll check for square bracket, we'll check for dot, whatever. So all these, like this is basically unary operators on the right, basically. And this is where we'll also do unary operator on the left. Unary operators on the left. This will handle the unary operators on the left. But I think this should be it. Let's check. That's correct. We have 4. Let's check if our Fibonacci is working correctly. That is correct. Factorial working correctly. Perfect. So now we have function calls also handled in this. So we have this handled. We have these handled. We have these handled. And these handled. We should also handle these eventually. Yeah, we'll do that. Logical or bitwise and all this stuff. So this is great. I'm gonna quickly get some water, get a bathroom break. So I'll be back in like 5-10 minutes, let's say 10 minutes. So let's continue at 12:20. And whoever is watching, thanks for still sticking around. I'll be back in like 10 minutes. Let's see. All right, we're back. I just got some water. It's tea. It's some nice Earl Grey tree. Okay, let's go back to where we were. What's the last thing we implemented? This is taking a little to remember. So yeah, we have Fibonacci and factorial working correctly, which is great, which means function calls are working. We should add a few operators, like we should add at least these, if not anything else, so that we can do like and or and stuff. And fortunately, that's very easy for us because all we have to do is add them to this table, binary operator table. I'm just going to move things around a little bit so that they are in order. Like token plus should be here, right? Precedence wise, not wait, how is not equals 3? It should be 7, right? Not equals to 7, yeah. Okay. And then 6 needs to, so 3, 4, 6, 7, right? Wait, this is completely out of order. It should be here. Okay, yeah, this is much more sense. So this needs to be here. Okay, just to maintain some sanity. Okay, so we should do 11 and 12 first. Yeah, let's do 11. So we have quad. Do we have tokens for it? We have amp. Do we have double amp? We do not. Do we have or? I guess we never added this. Okay, we'll add this here. Q token and so this is just 26. That's the cool part of our encoding. Is or 7C. Oh, but this might not be parsed correctly. Let's look at the ASCII table. So or is here, and that's fine. Yeah, okay, or is fine. I was worried about like these because they happen to lie between the identifier range and we haven't handled this separately. So this will have to eventually, square bracket and backward slash will have to eventually be handled properly. Underscore is fine. Backticks, I guess backticks are just not a valid C key, like let character, so we don't really care. Also, this is a lot of ads on this website. What the hell, Adobe? What's going on? Yeah, I should just have this saved somewhere. Is there a text version of this I can just store? Code chart. Oh, grid compact. Can I? Oh wait, this is Windows 1252. I don't want the whole thing. Why is it so weird? This is just annoying to copy. It's fine. I wanted something I can just like store it in a text file so I don't have to look this up every single time. Yeah, ask Gemini. Can you list all the ASCII code from 0 to 55 in a text table? not alphanumeric. I want FD. Oh, we don't want extended ASCII, do we? No, we don't want extended ASCII. So just, God, can you just make one table for 0 to 128? Yeah, this is useful. This way I don't have to look everything up again and again and again. So why is this double column? Oh my God. Why is this double column? Life is hard. You have to ask stuff to AI. Okay. This is good. Just up to 95. Oh, it's not double column either. It's 4 columns. Jeez. Sorry, give me a second. Let me just clean this up a little bit. Okay, this looks correct to me. Wonderful. You can also search things in this if needed. Okay, let's go back. So we were writing the defs. Yeah. So we have and we have or. These tokens need to go anywhere? No. Keywords are identified directly. Okay, so now we just need to add entries here. Token and precedence 11. Quad, some instructions for it. Quad token or 12. Okay. Now let's unit code for this. So this should be easy because all we need to do is take the and of the two expressions. And the way we do that is do the and check if it's not 0 here. We can do the and. We can't do bitwise and, right? Because those values might be integers. So we have to do logical and. Okay. Here. So we usually have it in RAX and RBX, right? Yeah, okay. So how do I do logical and of two integers in x86 64 No, but this is going to be bitwise, right? This is bitwise and I need logical and. Okay, so there's not a single way to do it. We first test each register and then convert it to a single, like we move it to the lowest bit and then do an AND. It's going to be a long instruction sequence. We're doing test set. Why is it moves 0 BL? Oh, because you're setting only CL. God, this is annoying. No, we actually don't need to do moves this because we can do the AND of AL and CL. So that way it should be fine, yeah. Okay, so what this is doing is test RAX set AL. Isn't there a better way to do this? Oh, do jumps. Also, this needs to have short circuiting behavior. So ampersand and OR are special in that they have short circuiting behavior, which means the second expression should not even be evaluated if the first expression is true. And the way we can handle that is in our parsing logic itself, we can basically check if like we'll have to generate code and then put a jump around it. Yeah, so these are going to have to be implemented differently. I hate this. Like this. Let's do it correctly. So these actually won't go into the table, I guess. Because if we do it using the table approach, then what happens is we don't get short circuiting because the expression is already evaluated. We have to write special cases for 11 and 12. Okay. Parse expert pre. Here. So the way this works is, let's go to the algorithm. So here we parse the first expression. At this point we check if 3 equals 11, which is AND. We generate code for this. We say generate if result, if not of result, jump, right? But this will unnecessarily generate it. We should do this only if the next token is and, right? So we should say if precedence equals 11 and get next token equals and then we want the short circuiting behavior. So if it is already false, we just jump to after, okay, and then this gets generated. So here this just becomes, so we have already checked the first one. We don't need to check that one. We can just check the same one again. So we can say generate if not of res jump after, right? Oh no, actually we can keep it like this. Sorry, this is a little annoying. This needs to go here. So if it's 11, let me do get next token equals. Yeah, if it is 11, we don't need to check this because the precedence matching already checks it. Okay, so 11 and 12 have to be handled separately. So this is saying is if it is 11, then generate if jump after. And then parse the next expression. This short-circuiting behavior is being annoying because the problem is we need to skip over this instructions if the first one itself is 0. You don't have to evaluate that. It's the annoying part. I hate this. Okay. If pre equals 11, jump after. What does this do next? Yeah, I think this will be fine. So what this is simply saying is, I think this should be enough. And then if we have seen jump, we just do after here. So we say right. So what this is saying is, if we ever needed to jump, then generate this jump. And we don't need to implement the and anymore because this consecutive checking of whether this is true and this is true and this is true is going to automatically ensure that the values are correct. However, we finally need to put the 0 or 1 onto the result stack. So jump then says generate push 0, right? And if it has gone through all these this is super frustrating because it has to jump over everything. Yeah, so then here it generates sorry, this is annoying. Push 1. over. Does this make sense? So is that if any point it's not true, then just jump to the end. I think we should be able to combine this properly though. I think there has to be, yeah. We can keep a running result. So we don't have to have all these things, right? Yeah, I think what we can do is we pop the value. And 11 has to be handled separately. It's annoying. Right? And this is saying is if not of res push 0. Actually, no, we can simplify this. We can simply say right, so we just push whatever the result is regardless. Okay, yeah, this is fine. So this will pop the result first, convert it into, okay, yeah, because we see an ampersand afterwards, it means that we should convert this into an integer value. So yeah, this is going to do the promotion, also do a quick check and jump to after. And this we don't need anymore. We don't need this either, we just need this. Yeah, so yeah, okay, this is good. So every one of these functions, every one of these will convert the result to higher. However, after the second one too, we need to convert. So if we have A and B, when B is eventually pushed in, this generate code for token will do that. So for ampersand, it will pop the old value, discard it, that's already been checked, and convert the second one into a boolean. Okay, great. This solves our issue. That's a little complicated, but I think this will work. Let's write this and see how it goes. So I'm gonna close some things which we don't need right now. We don't need tokenizer, we don't need driver, we don't need call, defs we need, ASCII, factorial, Fibonacci, don't need. Okay, let's do this. Okay, so after we have checked that the token matches our precedence, which happens here. We're about to generate code. Yeah, we have loaded this, we're about to generate code. So now let's check. Oh, but we can't before we call this, right? Yeah, right. Before we're about to call the next expression, we generate code for converting the top value into its like Boolean value. So we say compare Q RSI with $11. Jump on not equal pass expert no short circuit. Pass expert no short circuit. Okay. So we see an operator. So now we generate code for short circuiting. The result and short circuit. Okay. So first we need to boolify. So do pop RAX test Q. Oh, pop RX. Yes, there's no assignments. This is fine. Test Q RAX set we want truthiness, so this is being set by here. Check if RX is 0. Set not equals, yeah, set not equals percent AL, yeah. Actually we can do it in CL because CL is already zeroed out, right? Yeah, no, not here. I guess we do this then. And then we also do push RAX. So this has the new the booleanified value pushed onto the stack, and then we also push 0, right, the null pointer. Now we check if RX 0, the flag should already be set. Making sure that you're not corrupting the flags. Okay. Now we can do jump on equal, which says jump on equal says this is 0. Yeah. So now we could skip just over one instruction and generate like, so what we could do here is instead of putting this here, we could do like this, right? But this is better because this jumps everything in a single skip, which is great. Yeah, so yeah, the jump will have to calculate the offsets and everything, so that needs to happen over here. And then I do NOP skip forward, right? Yeah, so it'll skip all the clauses together. Let's copy this over here. Actually, this will have to change. It's fine, we'll do it later. When we add OR, we'll have to change that. Sorry, I'm just a little tired. Okay. This is a long sequence. Excuse me. Okay, so boolify. Is boolify a correct word? I don't know. Okay, so start writing them. We can write these 5. How many are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we can write all of these together. And I'm guessing this 81, this 2 is just how many bytes ahead. Okay. Wait, no, we can't do this. It has to be a long jump. Dot R, what is it? R dot T32. We have to use a 32-bit displacement because it might be longer. So it is actually this. Okay. Now this is precisely 16, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. Move Q. I could do it as 4 by now. This is single one is better. So 1, 2, 3, 4, 5, 6, 7, 8. No, 840F 00 6A 50C0B60F. Something is wrong. Eight four zero F 006A 50C0B60F. C0 is one shot. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And why is this longer? Oh, it's not. It's correct. And now we leave space for the jump, but before that we store this address, right? So move Q %R14 into stack slot. Minus 40 RBP is jump slot. And we can use the jump slot address itself to know if it's 0, yeah. This goes into minus 40 of percent RBP. Oh, we forgot to make space. This would have crashed everything. Okay, great. So now we have ISI minus 8 RBP. This is good. And then we leave space. 4 of percent R14. Hey, I'm surprised it's only 2 bytes here. Skip forward is just 2 bytes. Oh, okay. The constant is just the difference of the address. Okay. So this booleanified the result, and then booleanified the result. Checked if it's 0 already, and then skipped over. Great. Yeah, the OR would have to be handled separately. We'll do that later. Okay. Oh no. And we still have to write the code for precedence. I'll go here. So after the second expression is generated, we also have to do the same check, which will actually happen here, right? No, it'll only happen if the token is ampersand ampersand. It's a little annoying. I think we should just implement separate jumps, because now there's multiple places that need to be patched to jump to the end of it, and this is so annoying. I mean, we could make one jump at the beginning of it, which will go to the forward, and then, yeah. What we could do is write this somehow separately. Let's add a special case for 11, honestly. That's just best. (11) and 12 we'll add separately. So we start by parsing expert 10, right? If get next token equals ampersand ampersand, yeah, and this goes inside while 1 of booleanify. needs to be this way. Yeah, it needs to go after. But it also needs to check. God, this is so annoying. Now, is there a way to simplify this? Is there a way to turn this somehow into a simpler looking code? Right, so what we could do here is we could do yeah, so this will booleanify the last result, and that's all that matters. There's nothing more to skip. Okay, perfect. This is fine. So what we had before was okay, we don't need a special case. It's just this generate code for token would be empty. We don't need to do anything for this. Right? We'll pass the expression and just keep the result. It'll finally get booleanified. We could also put the booleanification logic here. Maybe that's easy. Yeah, that's fine. Yeah, so we can generate code for token. We'll just make it booleanified. And the and has been already checked because of the first one. Yeah, the short circuiting will make sure that the and is okay. This is great. So now we go to the table. We actually need to add this. Token and so what goes in here is just booleanification. So pops have already been done. We just need to do set NE, move this and push. I think the push null pointer is already there. Yeah, push null pointer is already there. So okay, so we just need to encode up to which register gets pushed. Okay, so we just need basically this. No, do we need test2? Yeah, we pop the value, we do these 3 instructions. So no, till here. Yeah, this should work. Oh, but it's gonna think it's a binary operator, which it is because the first one's result is still there. Yeah, this is right. The second one is gonna be an RBX though, not an RAX. What order do we pop? Is sub. We do pop RBX pop so it's an RX. Okay, so we just have to generate these 4 instructions. Yeah, okay, and we already have the code for it. Just this. Okay, so how many bytes is it? Of course, it's 10. Can we do it in less? Yes, we can by doing. So you don't have to sign extend, and we can do RCX. Okay, this is what we need then. Great. This is exactly 7 bytes. Perfect. '51 C1950 FC08548. Perfect. I mean, honestly, I should just make this table have variable length. This is fine for now. Okay. So token and we'll just finding it very hard to remember names of the variable functions now. Here. So this will parse the second expression, next expression. This will booleanify it automatically with some extra zeroing, but that's fine. That's correct, and it will go back to the next one. Okay, so this will jump back to the next one, and if the token doesn't match, okay, so the only thing we have to do is, we have already done this, right? Token is matched, we jump, and done. The only thing is now there's going to be multiple of these jumps that need to be patched. Yeah, there's going to be, as we keep collecting those ampersands, there's going to be multiple jumps that we'll have to keep patching. So one way to handle this is we could put this here, right? So it'll just literally patch the last jump. God, I'm so frustrated. No, this is wrong. This is going to generate booleanification twice. I hate this. This actually doesn't do anything. This needs to go here. Oh God, I hate this. So this will just be a no-op. This will have to booleanify the last one. Yeah, what this will do is simply just not do anything. It will just pop off both the results and push the second one. Yeah. It's just the first one needs to be handled separately. The problem is this. This is here because the first one needed this to be generated, but the second one onwards we don't need it because we can't do it as part of this. This is what I hate. Right? I'm so tired of this. Okay. Fine, we'll just leave it empty. That's what we'll do. We'll just put the same result back, and if it needs a jump at the end, we'll just booleanify it, and that's fine. Yeah, okay. Fine. This will booleanify the final result. And everything intermediate gets booleanified here. So we actually don't generate this code here. Oh god. Where's the parser table? This actually doesn't do anything other than just pushing R. AX or BX? Second one is RAX, right? Wait, RAX is at the top. Oh god, I'm making so many mistakes today. So it should be RBX. Just push RBX is all we need. This whole thing is not required. This is all we need to generate. $53. Okay, so this will do is just take the two values and push the second one. So you just like swap, yeah. There'll be two expressions at the top. It will convert the second one as the right value. This is great. Yeah. And as it goes back to the loop, when it goes back, this will booleanify it. If it's false, it will jump to the end, which is okay. And I absolutely hate this. I think short circuiting is so hard. Let's think. What if we did something extra here? If precedence equals 11 and get next token equals ampersand. Generate booleanify res. Generate an extra condition. I handle it separately. If generate before we enter the while loop, we check if next token is this. Now we don't need this anymore. For ampersand, this will do the booleanification and also the jump forward. What is the precedence for 11? And this is just go back. Oh god, I hate this. Okay, this is fine. I think this is okay. And then we can just return from here. Yeah. Okay, so we have to do a special case for this. This is fine. 11 and 12 need to be handled separately. Okay. The only issue now is there's going to be multiple jumps that jump forward. Instead of handling this, what we do is we do if not of res jump after, and we put before here. So these will just jump to before, and before will jump to after. And the benefit of this is we don't need to like go and patch multiple jumps in the back. We only have to patch one jump, which is this. Okay, I'll be back in a minute and continue on this. continue. Okay, so I think this is kind. We'll have to change this again. Actually, we don't need a token and anymore. We need a special case it. It's fine. So here we call the previous expression, and now we check. We check if the precedence is 11. Actually, can we simplify this too? It needs a separate code anyway. So this needs jump is not required. So this is fine. Yeah. Eleven is and right? Yeah. If it's 11. Jump on not equal. Let's just handle 12 here right now. No, can't do this. It has to be handled. Okay, so actually, let's just, if it's 11, we go to parse expert pre-11. Yep, which will finish it wherever. And just do 12 here too. Parse pre-12. Maybe these can be handled together, but that's fine. This is not required. Yeah, this is fine. We don't need this. Parse expression pre next. Yeah, okay, this is fine. Just need parse expression pre-11. Special cases. This is not a separate function. This is just continuation from here. Okay, so it is 11. Now we check if the token is ampersand, right? Yep. Yeah, ampersand and yeah. If the next one is not and, then we can just finish. Otherwise, we generate code. So what do we generate now? We generate first booleanification. This needs to be changed a little bit. So we do pop test extend push the new result, and we need to do jump skip forward, jump on not on jump on jump skip forward, jump on not equal, continue. Yeah, this can be fine. This can be a short jump. It doesn't have to be a long jump because you're skipping only over this. This has to be a long jump. Yeah. So, and then we can store the address of this one. So all the forward jumps can just come back to this jump. Yeah. Sorry folks, this is taking a lot more time than I was hoping this would take, but short circuiting is hard apparently. Yeah, okay, so we generate code for this now. Okay. Why is this a long what? Okay. Let's do this. How many bytes do we have? 1, 2, 5, 8, 11, 12, 13, 14, 15, 16. Okay, this is perfect actually. So we do the first 16 ones. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now we have done the jump to, we need to store this address of this jump basically. This 1 byte. Okay. Jump slot address, jump instruction address, and -48. Actually, you just use the same one, right? The jump, yeah, you just take the jump address and add 1 byte to it. It's literally the next instruction. Why are we storing it twice? Yeah, here we literally just stored this value here. Why move it again? This can be done. Okay, great. So we unified the first value, inserted a forward jump to the end, and created a label there. Okay, great. Now we do this. This is 11, so it must be 10. Yeah. Yeah, now we can call for 10, right? And then check, regardless of what the result is, booleanify it. Okay. So booleanification is just this, right? Actually, we booleanify, and if it's not equal, we jump back. That's fine. I'll take care of that. Okay. I guess the first instruction is the exact same, so this goes exactly as it is. For the next two, it starts from 006A. Yeah, so the 5775 has to be skipped. That's okay, we can just make it 0000. Yeah, this time we only shift by 14 because these two instructions are not there. And now we need a backward jump with the right offset, and this will require us to do like the calculation that we did for like while loop, for example. Let's look at while loop. Yeah, it's this. No, this is unconditional. Fine, I decided. Should be JNE or it should be JE? Yeah, this should be JE. This one. I got 7F. We'll do the math for that later. Okay, so how is that calculated? It's 868788, and this is 8D, 7D, 7D and 88. Work 7D minus 0x88 is minus 11. Actually, let's do 0x88 minus 0x7D is 11. Hex of 11 is 0xb. What is the 32-bit encoding of minus 11 in 2's complement? Just give me the answer, man. It's 0FFFF5. But we got FFFF3. What would it be for 0x? I think it's minus 9. No, minus 4. It's minus 13, right? I don't know how this minus 13 is calculated, because it's not 86. This is 86 and this is 7D. Oh no, 7F. Why did we do 7D, 7F? So okay, let's do 86 minus 7D. Is that minus 13? Yes, 86 minus 0x7D is 9, and so 8. Oh, I did it correctly. Yeah, I thought I did 7F. Okay. No, 7F. God, I'm an idiot. Minus 9. 86 is minus 7. So if I do 8 minus 4, no, plus 4, that is 13. Okay, so it's at the end of the address, whatever that value is. Okay, so I do 0x7f minus 0x88 minus 4. Okay. So we first do 2 of R14 into R14. Now I need to subtract, no, we first load that value, so minus 40 of percent RBP into RAX. Now we want to do R14 minus RAX and store it in RAX, right? So yeah, explain. I keep forgetting the order. Subq instruction x64. Destination equals to destination minus source. Fine. So destination equals destination minus 4, then we do add q, no, subtract q. Destination equals destination minus source. Okay, so this is wrong. Yep. Okay, so this is the address of the store. Now do move q, move l percent ex at R14, and then we do 4% R14. Perfect. So this will generate the backward jump to that forward jump, which is unfortunately what we have to do because we can't keep track of every single one of them. And now we simply do jump to parse expr pre11 next. I need to check if it's this. So yeah, this is fine. So if it's not, and we jump to parse expr pre-finish. Not yet. Parse expr pre11 next. Okay. Yeah. This will go to the next one, and then ampersand. This is correct. And if it's not, then we first have to return token generate after return. Okay. So we generate after. The return token can be done by expr continue. We already have that code there. So we just have to do generate the patch the target for the forward jump. Forward jump. Okay. this one, right? Yeah, skip forward. So let's see how does this work. So we are currently here, so at 8C, and the address we have is 7F. Yeah. So we do 8C minus 7F, right? Yep, 8C minus 7F. That's 13. Do minus 4. That's 9. Actually, just do minus 5. 8. Yeah. That gives us the value that needs to go here. Okay. Great. So destination equals to destination minus source, right? Yep. So move Q R14 into RAX, move Q minus 40 of RBP into RBX, move Q, sub Q RAX, RBX, RAX, sub Q $5 RAX, move Q, move L, present EAX at 1 of RBX. This is the forward. You have patched the forward, and now we simply do jump to parse expert finish. It just takes the token from the stack and returns it. Great. And we have started the token stack. Pass the target for the forward jump. This looks correct. I forgot to push null pointers, otherwise this is gonna break. Okay, let's fix that. So up the two values. Oh, right, I do have it. I do have 6A00 and 6A00. Okay, let's just push null pointer. Yeah, I think this is it. Finally have 643. Six 664. 670. Parse expert pre continue and define reference to parse expert pre 12. Okay. Let's make sure everything is working correctly first, which is Fibonacci should tell us that. Okay, great. Now let's write a simple case for short circuiting. And int side effect. Put char 65. No, where were? 97. Return doesn't matter what. And now we do return 5 and side effect. So this time the side effect should happen. What does it say? Examples. Okay. Okay. The side effect didn't happen. And 5 just got returned as it is. What the hell happened here? Do I not start from the right precedence? I guess 14 directly jumps to 7. We need to jump to 12. Yeah. 6 pre-14. Yeah, this one sums to 7. This one goes to 11 now. Still returning 5. This should go to 12, not 11, but okay, let's see what happens here. So this parses the expression. If it's 2, it parses integer, identifier, whatever. Okay, this one actually calls the lower one. If it's, never compared the precedence. Okay, we got the side effect and we got 1. Perfect. And if it was 0, it should not happen. Please. It did not happen. Yes. Wait, why is the error code not 0? What did it return? 0. Yeah. Okay. Great. We have short circuiting working. I want to test another one too. And side effect of. Let's actually make it functional. Side effect 2. Just call it side effect 2. This one returns 1. And just call side effect. Right? That's fine. And so none of these should evaluate. That's great. But if it does return 1, then it does create both. And if I happen to put a 0 in the middle, then it returns 1. Perfect. This was great. We do have our short circuiting working correctly. This took a while, but everything's working correctly now. Okay, now let's go and change our Fibonacci to actually use ampersand, ampersand. Oh, we don't have OR yet. So let's do OR. This should be very similar, except for like jump on, like the set would just change. That's it. That's it. The set is all that's going to change. The set NE becomes set E. That's it. Okay, let's go to 6 per 3, 11 and 12. Okay, so I guess should I just copy over the same code? This is a big function. Fine, I'll just copy it. Who cares? So this goes exactly the same. Instead of this becomes OR. Okay, so now we pop the results, we check, and we okay, so this just becomes jump on equal, right? Jump on not equal continues. On jump on equal, it's just going to say, hey, if it is 0, you need to check, otherwise you can just return, skip forward and return. Yeah, so this becomes jump on equal, and the backward jump, which was here, also becomes jump on equal. No, wait, not this one. This one becomes jump on not equal. Okay, so these just get swapped around. Okay, so let's go here and generate jump on equal. Next inf jump.d32 can be anything, I don't care. Skip forward, NOP, and then jump on not equal dot d32 forward jump address, and this is just next. This is exactly the same. I just need the encoding for these two. Yeah, JE became JNE and JNE became JE. Well, I wanted to get to writing ELFs. I can still do that. Yeah, it's just 2 p.m. I have 3 more hours to write that. So JE is 74. I'm just gonna copy this. Yeah, 675 becomes 74, and 0F84 becomes 0885. Wait, isn't this wrong? No, this is right. And then what's the other one? 0F85. 0F84 becomes 0F85, which was, oh, I haven't copied that yet. Okay, so I've only copied it till Yeah, this is correct. Let's try OR now. So it did AA. So the way this got evaluated is 1 1 0. So this did go to the second one and it returned 1. And if I change this to 1, it should not. Only printed 1. Perfect. And if I just made, no, this doesn't really matter. So if I did 1 or, nothing should be printed, right? Nothing gets printed and everything is correct. Okay, so side effect is correct. Now we go and change Fibonacci to now just simply say x equals 0 or x equals 1. Yep. Fibonacci prints 13, everything is good. We can also now change, because we have precedence now, we can do this. Is also correct. Wonderful. So we have precedence working, we have OR operators, logical operators working, and we also have short circuiting working. Now, I wanted to do unary operators like ampersand and star. I want to do plus plus. That's fine, we can skip that. These might be useful. And these we don't need. This is like a proof of, I mean, eventually we'll add. Should be easy to add. They're just like binary operators with some precedence. And the instructions are reasonably straightforward. It's just ands or. Okay, let's skip this for now and let's switch to the fun part, which is ELF generation. So far, what we have been doing, actually, before we do that, I'm gonna clean stuff up a little bit, remove code that we don't need. So this one we need, this one we need. This one we need. Where is parse binary operator end being called from? Okay, that's being called here. Let's call it check binary operator end. I'm going to move parsing of variables expressions into a separate file. This is getting too complicated. Check is type return. Yeah. Parse expr.s. Sorry. So let's move stuff. Okay. So these expert 14 next, pre expert continue, pre and pre continue, pre finish, pre 12, 11, check binary operator, integer identifier, expert local, global, function call, goes into here, and the binary operator table is also going to be moved. Right, we just have to make this global and tell it to put stuff into the text section. I don't think I need push null pointer here, do I? Yeah, so just move it there. And LTES, GTES, this is required here. Relocation against token assign. Invalid expert len. Invalid identifier. Check local table, check global table. Cannot resolve GTES, LTES. This actually needs to go into defs now. Undefined symbol to local symbol table end. Great. We commit everything. Fibonacci, def, source, parser, example precedence, example short circuit, SRC parse. Working operator precedence, short circuiting of and okay. Now let's focus on ELFs. So what we have been doing, okay, I'm going to close some things. Okay, let's look at execution area. So we have so far just allocated this giant piece of chunk here, which is code gen buffer, in the like a special executable slash writable and readable section, and then we just jump to that, right? This is fine, but ideally what we want is to generate an executable. So we want to say like, hey, compile this Fibonacci.c and generate Fibonacci.exe out of it. The annoying part is to be able to execute executables on Linux, they have to have a right set of headers. You can execute raw binaries too. It's just annoying, and it would be good to have an executable generated. So what we're going to do is we're going to prepare an ELF executable and write that to a file. Now, Generating an ELF executable requires you writing ELF headers. I have actually done this in the past. I minimal ELF. Yeah, so I have written this program, wrote this program a long time ago, which basically creates a minimal ELF header with a text readable, writable, executable section, and then generates a file out of it. Okay. The way this works is you can write a program.s like this, like it's a simple program that starts from start, prints hello world, right? And then I have a make file which generates, this one generates a template from a C program. So I also have a C program version that generates, this is like just a C program that generates hello world using system calls, and it generates the start function. Okay. And what we are doing next is creating this ELF gen, which just compiles elf.c. And then we generate the program by calling elf gen on the program template. Now this program template is the set of instructions that come out of this basically. You see how I'm first compiling it into a .o file, extracting the text section out of it by saying give me an output binary of the section .text into this program t. This program t is essentially just a raw binary which just has the sequence of instructions. And then I call elf gen on it and generate the program that I can then just execute. So yeah, if I do make, it generates this program which prints hello world. And this file is actually pretty small. If you look at the headers, it's just 169 bytes. So this is like one of the smallest hello world printing programs you can write. It's not a complete ELF by any means. Like you don't have debug symbols, you don't have unwind information, nothing is basically there here, but all it has is an executable program. But that's basically what we need, right? We just want to be able to package our code that we generated and data section that we generated into a place that we can execute. So the fun thing about this is we prepare all the headers here, right? So let's look at this elf.c and how I wrote it. So there's basically just a bunch of type defs here, so it's just different types of word and half and address and so on. But there's two main structs that we have. So there is the elf64 header. So this one of this exists for the whole file. This one basically says, hey, this is an ELF file, and here are sort of the information about this file. And then there is the elfp header, which is for each section in your, actually, is it called section? I think it's called section. Yeah, so each section of the ELF, here's the information about it. And it has a bunch of like fields that we care about. And what this one is doing is loads the program template, then assembles the headers. So the way it does that is by first loading the template, then it creates, it allocates a buffer first. So here I'm calculating total size. So total size is ELF header plus one program table with one entry. So it's like one section header. And then you add the actual program section, which is the size of the program. Then you allocate the total buffer, write the headers to it. And the way I'm doing that is by like setting individual fields here. So you'll see there's like executable type, executable machine, like AMD64, version, then where does the program start executing, and like header offset, and then some bunch of flags and so on and so on and so on and so on. Good thing is a lot of these are just constants, which means we can just bake them inside our program as data. So we don't have to like assemble this bit by bit. There's only few things that need to be changed. Like for example, this v-adder, for example, is where the program chosen virtual address for the execute, like where does it start executing? That needs to be set properly. Then program size needs to be set properly to say how big the section is and so on. There's a few things that need to be like set, but other than that, everything is just like yeah, it's just constant data. So we can pre-bake this into our ELF headers and just generate it. So that's what I'm going to do now. And the only section that we have is this one, which has the flags read, write, and execute. So we don't have to worry about it. Let's look at how the generated ELF looks like. So if I just do obj dump, actually no, I just do read ELF program, need some flags, and just do all, yeah, read ELF dash A. You'll notice that it has a bunch of headers. So first it has the ELF headers, which has the ELF magic string, which is basically a string saying, hey, this is an ELF file. That's like a fixed constant you have to bake in. And then it has a bunch of information like the OS, the ABI, it's an executable file versus it's an object file, what machine it's running on. Basically all the data that we put in came in here. And then you have the entry point address. Start of program headers at 64 byte into the file. Let's also look at how this file looks like. I think hexedit. I don't have hexedit installed. Let's ask Gemini. How do I dump the bytes in a file as hex dump? I do have hex dump. Okay, so yeah, this is basically what the 64 byte headers are. We will try to still like construct this line by line. So let's go to our execution area, because this is where all our headers will be assembled. And let's start in the data section to like create a template of the headers. So we'll say ELF header oh, why am I capitalizing it? ELF template header, right? This is where we start. So let's actually minimal ELF, not miniconda, minimal ELF, ELF.c. Okay, so the first thing is a 16 byte magic string. So let's put that. It can be 2 quads. And the value is, because it's a quad, it has to be written in the reverse order. Yeah, this is what it is. 1, 2, yeah, 8 bytes, right? X01, 00, 02, 01, 4C, 46, 7, F, 4, 5. I'm also going to put comments on what this is. This is ELF magic string. I think the rest is all zeros, right? Yep, zero. So it can just be 0. 01, 00, 21, yeah. What's next? Next we have E-type, which is a half. Now half is a 16 bit constant, but we can combine these two. So we have 2 halves, right? So that will be a 32 bit constant. We have type and machine. So let's do type and machine long. Oops, sorry. So what are the next 2 bytes? We have this constant, right? 0x3e 00 02 00, right? Actually, we can just look at the code that generates it instead of me trying to like look at the bytes and do it. Yeah, this one is ident, which is fine. Somewhere I must be, yeah, here. So machine type, all these constants are here, so I can just like put them in. Yeah, this is better. But I need them side by side, so I could just copy this for now. paste it here. Okay, so actually let's do the right way. Instead of merging them, let's do one by one. So I need a, this is just short, right? Yeah. So the short is 2. Then we have machine, which is also short 62, right? Yeah, 62. Then version is a word, and word is 32. So it's just going to be a long. Version dot long. Version is set to 1. Then we have, actually let's just fill in the values later. Let's create the address. So address entry, yeah, let's fill in the values later. This is a quad. Then we have ph off, which is 64 again. Off. Then we have offset is 64, right? Yeah, offset is 64. Sh off is also 64. Sh off is quad 0. Then we have a word, so 32 bytes of e flags, 32 bits of e flags. E flags dot quad, no, not quad, 0. Then you have halves are 16 bits, so short. You have, copy this here. This would have been much easier if I had to. Okay, so let's say short 0 dot short 0 dot short 0 dot short 0. Let's, I guess, also put types for these. So type went here, machine went here, version went here, entry went here. So I should have thought of this before. So we have types 2 now. Okay, great. Now let's go and fill in the values. Okay, so we did type 2, machine 62, version 1. Entry needs to be computed, so entry we'll have to leave as it is. So we'll say elf template header entry e underscore entry, right? And we'll use this label to then fill in the values. Okay, then we have ph offset. What was ph offset? Ph offset was total size. So this is where the ELF header ends, right? Yeah, so this is easy. So we do ph template header. So ph offset just becomes ph template header minus elf template header. So it's a constant. Great. So we have ph offset. SHOF is 0. E flags are process specific 0 for LD produced binaries. Wait, really? E flags is 0? Okay. Then we have EH size, which is size of header. Now this we actually need to compute. I think it is 64, but we can dump it from there. And then ph end size is size of ph header, which will also be some computed. Ph num is going to be 1. So you just have one program header. SH end size 0 and SSH num is 0. What the hell is SH strndx? SH strndx. Never initialized, so probably 0. Okay. So we just need to put the EH size and PH end size in it now. And the easiest way to do that is just change this code and ask it to print it for us. So I'm just going to print at the very beginning, print f size of ELF 64 E header equals person D n comma size of ELF 64 E header. For P header is also equals to P header. Yeah, it's fine. 64 and 56. So EH size is 64, 56. Great. Hey, is that correct? 64 and 56. Okay, great. And that's what we put in, right? Slar header is ELF64 header. Great. So we have our E header template completed. Now we do the P header, which is this one. Okay, so it's a word. So word is what? Long. Offset is quad. Address is quad. Address is quad. X word. What the hell is X word? Even 6040. This is extended word. Okay, now we need to fill in these constant too. So let's go to the section where I'm filling in the P headers. Okay, so P type. P type is 1. P flags 1 or 2 or 4. So this is what? 1 or 2 is 3, 3 or 4 is 7. P offset is program offset. So this is a little tricky. Chosen virtual address for executable is vadder start plus program offset. What is the difference between these two? Let's check. Program offset is where in the header does the program start, right? So this is just program offset is total size after the headers. Okay, so what we're going to do is ph template end. So this is going to be ph template end minus elf template header. vadder. Now vadder needs to be computed based on the load address, right? It's vadder start. I think vadder start is where this program gets loaded. Yeah. Yeah, vAddress start is basically where the ELF should be loaded. So now we have to be very careful with this. What we're going to do is we're going to actually set it to CodeGen area, CodeGen buffer plus ph template n minus elf template header. And hopefully this allows parentheses, so this should be fine. So what we're doing is basically, if this was in the CodeGen buffer, where would the program start? And that's this vAddr start plus program offset. P-adder is just 0. I don't know what that is. I don't remember. Program size needs to be filled in. So we say ph template header program size, and program size is the actual number of bytes of the program, yeah, which is similar to what we had here. So e-entry is where the program execution starts. This will be the address of main, basically, we'll have to fill in. And this is program size. Okay, this is fine. Mem size is p header of p file size, so it's the same. So I have to fill in the same value in both the places. And align is just page align, and page align was 4096. So this is, since we are specifying a specific like address for loading, I think this shouldn't matter. Yes, somewhere we need to have to specify where the executable needs to be loaded. Right, there has to be somewhere where I say vAddr needs to be added. No, I guess the program header is what matters, because you can have multiple programs inside the same ELF, and yeah, it's not really sections, it's just a program header. Yeah. Okay, so you can have multiple program headers, and all that matters is where that particular program header is loaded. Great. Yeah, this will ensure that the program header is loaded at the right position. Program size is correct, program file size is also correct, and p align. Yeah, page align. This says no alignment requirement, but that's fine because the vAddr start actually, so what we need to do is we need to say this also needs to be aligned to 4096, which is execution area. The buffer that we are creating needs to be aligned, which it will be because it's in a separate section. Honestly, now this doesn't need to be writable. This can just be like executable. It can just be write. So this can be in section data. Actually, no, this will be in section BSS because we don't want this to take up space. But I need to align this. In GSM, how do I align a label? So what is the argument for B-align? Is just the alignment itself? Yeah, okay. And 4096. Let's make sure that like the cogent buffer also starts from the right address. Okay, this is great. So we'll have to put this back into the yeah. And now we simply say dot equ elf header size comma dot minus, what is it called, elf template header. Okay, and now what we need to do is we need to, from the driver, we need to, before we start writing the program, we need to prepare this. So we are program source has been loaded into R14. We do the right program source in R14, and before we start calling parse tu, we just need to say call prepare execution area, right? Now prepare execution area, what this will do is this will slap the headers into the right place. So prepare execution area in GSM, can you give me a sequence of instruction to copy over a fixed number of bytes from one buffer to another. Yeah. Just do a string copy. Okay, so leaq code gen area of %rip into %r14. This will do what we just removed from the driver, or it was code gen buffer. Let us code gen buffer. Next we move that to RDI2. LEA. And then source will be ELF template header Okay, and then we do size. The size cannot be bigger than 32 bits, so it's fine. ELF header size. CX, and then we just do rep move SB. Okay, so this will have copied our I mean, there's a faster way to do this. Yeah, you can do like SIMD, you can do register copies, but it's just fine. It's like very small anyway. It's like what, 64 plus 56 bytes, so it's not that much. Okay, this will advance. Actually, we should do this right. This should go here, this should go here, and then we finally move to %RDI into R14. Because RDI gets advanced, right? Yeah, we should CLD it. Make sure that it's advancing in the right direction. Okay, and this is correct. CX becomes 0. That's okay. Okay, so now we have our execution area prepared, which means we have copied over the ELF headers. We also need to do execution area finalize. Now execution area finalize will go and patch in the addresses. So we have a couple of things to feed in. So we'll have ELF template header e-entry, which is the entry point of the program. So this we'll have to patch later. Let's do the size first. P offset is fine. This template header program size, ph template header program size. This is the program size we have to fill in. So we need to first compute the program size. And what was the program size we filled in? It was just program size, not including the headers. Okay, so we need to compute the program size first. So in R14 we have the end, right? Destination equals to destination minus source. Remember that. Sub q. No, first we move q code gen buffer of %RIP into %RDI. Sub q RDI, R14. So R14 has the size of the program now, including the header. So you need to subtract sub q ELF header size of R14. And now we need to write this into this one. And we also need to write it again, because it has the same thing in file size and mem size, right? Yeah. And now we need to compute the address of main. So we had the execute program function. which goes and finds the address, right? So this is what looks for main. So we take global address, and at this point in RAX we have the address of main. So this goes here. Execution area finalize check next. This is fine. At this point we just write the address e-entry. Now e-entry in this case happens to just be v address start plus program offset, because in this case it's just a start of, because the only thing there is start, but for our case it's just going to be the complete absolute address. The address start plus program offset, so we will just put the address of main. So the trick we have done here is whatever address it was loaded at this section codegen buffer was in this file, we are loading it at the same address in the generated file. So that way we don't have to like move things around. Like all our absolute addresses, everything that we have inside our code will be fine. I mean, eventually we should move to relative addressing everywhere, but it will still work because we just have, yeah. And finally, this is done, and we need to have a separate function called, okay, so now this gets commented out. We don't execute jump program anymore. We do write to the file. Okay. So let's make sure that we have 3 arguments, not 2. Invoke as file name, output file name. Yeah. And now we write it out. So this time we open for writing. RBX has nothing. I'm gonna put this actually in a separate section. Make it into a global variable actually. Compiler args. Okay, so we just stored the compiler args for later. Okay, now we load the compiler args. And now we get the file name. 16, yeah, 16. To RDI, move queue. This is a open system call, right? Yeah. Flags need to be set correctly. And call. We have flags and we have mode. So we have to pass oCreate. and mode we have to pass read write, right? Okay. O create goes in flag. No, flags contains just read write. Mode. No, flags must include one of the following access modes. What is mode T then? The mode argument specifies the file mode bits to the applied to be when the file is created. Oh, this is great. We can put the executable right here, so you don't have to do a separate system call. Amazing. We want user to have write execute permission. Following constants are provided. User has execute. So I'm just gonna ask Gemini for this. First, let's do O read write. Actually, just O write should be fine. 'Yeah, we don't want append, async, close, exec, we want create, direct only. Yeah, these are 0x41. Okay, so we want I want the file to be executable for the user. What would the mode be? I think it's just going to be 744. Yeah, 744. 0x41 in move q $0x41 into rdx, right? Why is this RDI? It is RDI. RSI Q $0x744. This should be no, not 0x744. $0.874. Yeah, 07. Does this have octal encoding? I don't know. 484. Wait, is 41? Yeah, is syscall. So this opens the file, and file must be open. There's no issue really, and then we'll do the write system call. So I actually forgot. The size should be. We need to finalize execution area. So that is prepare execution area finalize. execution area finalize. The problem is the R14 is corrupted now, which I don't like. So R14. Okay. Now we will use the R to compute the size of this file. Okay, so we have opened the file. Now we need to write syscall. So it's count file disk. Jesus, why is count first? That seems wrong. FD is first. Yeah, this is wrong. Wait, what the hell? Am I hallucinating here? What? Is man 7 broken? What is happening? How is this? RX is call number 1. Okay. Move Q. I need to compute the size of it first. So move Q R14 into RX sub Q no. Q code gen buffer into RPX sub Q RPX REX. So this time we don't subtract the header size because the header size is to be written to. So this goes to file descriptor 1. That must, oh shit, we overrode the file descriptor. Let's move the file descriptor to the right place. RDI. I wonder if the file descriptor argument would change. I don't think it should change. Syscall should preserve registers. Yeah. Okay, so RDI has the file descriptor buffer address. We already have it in RBX, right? Yeah, okay. So the better, okay, this is going into buffer address is going to RSI. So I'll just put it into RSI directly. Okay, so RSI already has the start address. RDX has the count. Okay. And finally we write the system call number. So move Q $1 into RAX, right? Yep, and then syscall. And finally we need to close the file, which is here. And RDI already contains the syscall number. Perfect. And I think this should just work. At this point we can just do ret q. We have Do we need leave? No. Okay. Yeah, so now we are not executing the program, we are just like producing a file for it. To clean the errors first. Codegen buffer cannot be used when making PEI object to recompile with FPEI. Let's see, this is in tribal. Codegen buffer. It's here. Cannot make it global. It is global. Oh, it needs to be relative. Great. Let's check the simplest example that we have, which is empty. It doesn't need any standard library. And it prints bar equals to foo plus 225. 225. Okay. x86c example empty. And it does complain. So now we do I should put it somewhere else. Scratch / empty. Segmentation fault code dumped. Get token itself is failing. Interesting. Wait, this is new. Two two six zero. Wait, this is hella confusing. It's failing in. I think I just didn't prepare all the things properly. Did I load the program source? I did load the program source in R10. Nothing really has changed. Yeah, it seems fine. Oh, the only thing that's changed is prepare execution area. Does prepare execution area mess with some register? Shouldn't. Yeah, all it does is, I'm just gonna comment that out for now. Oh, but this also loads. No, this is fine. Fine. This is okay. No, why is this sec faulting? Is this correct? What did I change? Execution area finalize. It's failing inside parts to you, but I didn't even change anything. only change I did is this. Move RBX into compiler args of RIP. Compiler args of RIP is just here. Right? And we change the comparison to 2. That's the only thing I can see different. Did I do anything in tokenizer? Nope, change. Okay, let's just see why it complains. I can step through this. This is open, right? Three. Okay, so we did get it. This is the read system call, right? We got 61, so that must be the number of bytes. This seems correct. And this must close the file. Great. Loads program source into R10. We're going to check that. So p/x%r10 is a valid address. p/c$r10. Oh no. x$r10. Yeah, there's I. x/16 b$r10 int foo. This is correct. Next I si. Parse to calls get token. This is get token, right? Okay. Oh, the very first instruction of get token is failing. Which is token cache. Can I remove this? Well, it does exist. Token cache of RIP into RAX crashes. Like, this is insane. Why does it say function get token not defined? What? Oh, because it should be in text, not in data. Wait, how did this happen? How did suddenly? Oh, because I don't know. I didn't change the tokenizer, right? Maybe I changed it from earlier. I did remove that. Okay. That did it. Okay. So Trojan buffer, it jumps to for some reason. What? But I'm not executing the program. Why is it failing in Trojan buffer now? Why is it even going to Trojan buffer? It's checked. Oh, execution area finalize for some reason caused it to jump to the program. Execution area, prepare execution area. Execution area, finalize. This made some mistake. I don't see any mistakes. Just corrupted something. Okay, we'll step through it. So parse tu is fine. Now we step into execution area, finalize. Alright, why is it going to check next function? Oh god. Finalize, check next. Still going there. Oh, wait, did I not make it? Wait, what? I changed this. I didn't save it. Okay. And we must have gotten an empty now. Exec format error. Cannot execute binary file. Okay. Let's do hex dump empty. Well, this is obviously wrong because there's a bunch of zeros at the beginning. Ah, I know what happened. We did not do prepare. Here. Prepare execution area. Pass tu execution area, finalize, and this is fine. Wait, did I do make? Now it should be correct. Okay, this time it seems at least the headers have some sense of meaning. Okay, of course these are wrong. 457F, I guess I just typed it wrong. Oh yeah, it's completely screwed. Wait, how did I screw this up so bad? Oh, they're grouped by 4s. Man. I'm just going to check what this is supposed to be. It's supposed to start with x7f. Okay, so it is grouped by 2. Does hextemp have a flag to print like 1 byte? 1 byte char. Okay, this is what we wanted. Yeah. Okay, so first 8 bytes 0 0 0 1 0 1 0 2 4 6 4 5 7 F. Right? 0 0 0 1 0 1 0 2 4 6 4 5 7 F. Okay. 7F454C. Okay, this looks, no, this is still not correct. 4546. Where did 46 come from? 4C. I'm making stupid mistakes today. Okay, 7F454C 020101 double zero double zero. Wait, why is. Oh, there was 4C46. God. Okay, this time this is fine. 7F454C4602010100. Okay, this is correct. Now I can try to execute this. Segmentation for code dumped. Oh yeah, how's the weekend going? It's going well. We're in the middle of generating ELF executable, so we don't have to execute our program directly from the compiler. Um, it's going okay. I think it could be better, but it's going okay. RIP is 0 for some reason, which means we did not write the. So we can do read ELF on this. Might help. Read ELF empty, and we just do -a. Okay, and actually let's do side-by-side comparison. Read ELF program. Okay, so ELF header magic is correct. Class ELF64, 2's complemental endian, 1 Unix system V, OS ABI version, executable file, AMD's entry point address is 0 for some reason. Okay, this is a problem. 64 bytes into the file, bytes into file, flag, size of header, size of program headers. This is pretty cool. Oh, we have someone called Sir ELF man. It's not optimizing. Yeah, it's a C compiler in assembly, and the goal for doing this is to be able to write a compiler in assembly that compiles like very small subset of C, but use that to then write a full-fledged compiler for C or C++. I mean, probably C. I don't have the energy to write a C++ compiler, but yeah, it's like a bootstrapping process we are working on. And we have a working compiler. We just need to generate binaries, which is what is going wrong. I think entry point address is currently wrong. We will fix this. 64, this is fine. 0 0 0 64 65 56 1. This looks all correct to me. RWE alignment. Wait, why is align 0? Oh, supposed to be 4096. Okay, we will fix this. And this is probably the address of where it got loaded. Offset is 78, so that's correct. This seems to be correct. This also seems to be correct. I'm working on a compiler, but nothing. This is crazy. Haha. Yeah, I mean, this is not your typical compiler, right? Like the goals of modern compilers are optimizations, not writing a parser or not writing a code generator at this level, especially in assembly. This is just a fun exercise because, I mean, us compiler engineers I'm from my like context. My background is in compilers. I do compilers research. We assume that hey, a while ago some people wrote compilers, and I mean, in my mind, I always was like, yeah, they wrote it in assembly and they got it working, and I was like, I want to understand how that process looked like what were the struggles through it, and this is just like me doing this so I can understand it. Yeah. So I think the only mistake with our wait, there's a couple of mistakes. The file size is also 0. Did I not? Oh, I know what happened. I wrote these. The finalize did not write it at the right place. It wrote it at yes. So this math needs to be changed a little bit. We wrote this at ph template header program size, but this actually needs to be ph template header program size minus elf template header plus code gen buffer. Yeah, same for this one, minus elf template, because we have already copied over the stuff, right? Code gen buffer. Yeah, and same goes for this one, minus elf template header plus code. We just did not write it at the right place. We wrote it in the template. We have to write it into the actual like program that we have assembled. Hey, since you are a compiler engineer, what are some of the strategies optimizing out bounds checking? I'm throwing the tiniest possible byte sequences to making bound checking branchless and small. Yeah, so this is a good question. Let me just quickly finish this and make sure that this compiles, and then we can take that. Oh God. I'm gonna quickly read elf this time the entry point address is correct. Okay, so there's something else wrong. Okay, um, so what you're saying is, what are some of the strategies to optimizing out bound check? I'm throwing the tiniest possible byte sequences to making bound checking branchless and small. Um, yes, so it depends on what you want to do post bound checking. So again, this depends on the language. This depends on what kind of memory safety you have built into your language, right? Like the most extreme answer is if you're writing C, you don't do bound checking, so you don't have any branches. You just assume that whatever the user is doing is correct. The goal is to make the CPU address 0 and trigger a trap. Okay, so you want to be able to trap if the bounds is out. So there's multiple ways to handle this, honestly. You're probably going to do like a read or a write on the buffer, right? Like you're loading, in your case, it's basically for any bound check output XOR R0 compare R3, and then conditional move R0 R1. Yeah, so that's your current. Let's think about this. So the conditional move takes care of the fact that you are only copying it if it's within bounds, right? Yeah, so, but if it's not, you want to be able to trap. And you don't want to use the branch for that. Now, what are ways to trap? Is any kind of trap okay, or does it have to be like a jump to 0 trap, or like a what's it like C3 or something? Do you want any trap? Yeah. So if you want any trap, what you could do is write to an invalid address, right? Like you could write to a predefined invalid address. Like the conditional move, invert the conditional move. So what you could say is there a conditional move on not true, like conditional move on false? I don't want you to have to invert. Yeah, there is one. Okay, so you can just like do conditional move and then conditional not move. I mean, yeah, that requires a second comparison though. But if you could reuse the same flags, like basically invert the flags and then do a conditional move to a bad location, and that will immediately throw a trap, right? So what I'm suggesting is basically looking at my screen. You already have comparison R2, R3, right? Um, and then you're doing C move R0 into R1. This is fine. Uh, is there a what's the so the trap on the C move other than after it? Uh, I mean, it'll be after it, C, whatever the syntax is. I'm not sure. I haven't written. This is ARM, I'm guessing. In a while, you could do R0 to R5 when R5 is initialized to bad. Right now, because right now R0 is the output pointer to the array. Yeah, so you will do something like R5 comma R1. So every write is basically a normal move and followed by a conditional bad move. But the condition for that is inverted. So if it is correct, then it goes into the right buffer. If it's wrong, it immediately traps. Does that make sense? Or if you want it to be slightly safer, you could do it like this way. I mean, check first and then write. There are other ways to trap too. On ARM64, I use C-cell, which is one op. Let me look it up. Sorry. Can you explain C-cell in ARM64? Conditional select. Oh, so you're using conditional select for. Where are you using the C-cell for? For doing the bounce check, like in register, or for the actual storage? Compare. Oh, compare then C-cell. Okay, so you do compare and then C-cell for computing the address to write to. Yeah, so you could do that. Yeah. So what you could do is you could say compare and then C-cell here. Yeah. That seems right to me. Yeah. So you could like load either the correct address or the bad address conditionally, and then write that. Then you don't need the conditional move though. You can just do move here, right? Yeah. Yeah, having a zero register is really nice. All right. I hope that answers your question. This is my attempt to solve that problem. There are other probably better ways to do it too, but this should work. Anyway, let's go back to debugging why our program is not working. PDB empty. But this byte sequence got me to be around so fast or faster than what Luajit output, which is nice. You just tried it out? Is that what you're saying? Oh, great. I mean, please share the repo if you're allowed to. We can take a look at it too. I would love to see what you're working on. During startup, program terminable signal just like immediately terminates. No assembly available. No registers, nothing. Yeah, I'll take a look at this. It's a toy line, but still fun. Okay, I'll take a look at this in a bit. Let me get through debugging why my ELF generation is failing. RAX was the address of the global. Oh, I think I know what's happening. I think these headers are wrong. Read elf-a empty. Right? Like the start address seems good to me. No, the virtual address is also fine. 78 and 98. Why is the file size wrong? The hell? What's the file size negative? Okay, cochain buffer RIP into RDI. So that's the start of our cochain buffer. R14 goes into RAX, sub Q RDI RAX. That gives me the size in RAX, and then subtract the ELF header from it. ELF header size from RAX. That seems correct. And then I write let's put a breakpoint here and check it. I think this is something wrong. Yeah, the file size seems to be negative for some reason. Execution area finalize. Yeah, that's wrong. Let's do this again. This is execution buffer. Oh, I did move when I wanted to do lead. This was the issue. This was the issue. I'm doing a major rewrite of the API because, of course, I got an idea. Of course, yeah. Yeah. Okay, this worked correctly. God. Hey, at least we have something, which is good. Let's see. Of course, this is not gonna work, but frame one. All bad. How do I start execution with break? I guess I could do this. Read elf-a. Oh, you use GDB on Windows. I use Visual Studio as an assembly. This is Linux. This is I'm using WSL2, not using Windows natively, because all the stuff we are writing for is for Linux anyway. Like the compiler itself uses Linux system calls. The code we are generating is ELF, so it's all in Linux. I'm just using a Windows. Yeah, it's a systemv. Systemv and Linux both, because we're using the Linux API, which is for reading and writing files. That's not I guess that's not just systemv either. Some subset of it. Let's dump this. Why is this going all over? Okay, the file size is correct now, so that's great. Alignment is not great. Okay, let's look for alignment. Why is alignment not correct? Oh yeah, for some reason I left this uninitialized. Is that the reason? Couldn't be. Nope. Okay. Read elf-a empty. The starting address is this. I'm going to put a breakpoint on this. It did not breakpoint. In GDB, how do I break from the very start of the execution? Start I mean, that's basically what I did, but that did not work. Okay, it did stop at the right address. Oh, it's 7098, 8098. Wait, did I put the breakpoint at the wrong address? I did. I put on the Of course I did. Okay, so this is good. This is good. We have the oh yes, we tried to return from it. Yeah, so up to this point we could just write main, but now we can't write main. We have to write uh, the exit system call. So that way we can, yeah, yeah. This is a change we have to do. So let's get to the point where we actually now have to start putting stuff into the standard library. So let's open our x source x86 libc. Yeah, this is the one that we care about. Now we go global x86c libc underscore start, right? The problem is start doesn't really have the start. The address needs to of main needs to be patched in because some main comes after start. Okay, that's fine. We will do it as part of finalization. So this is a special function. Global x86c underscore libc underscore start. God, this is annoying. I was accidentally passing a 64-bit into a bool which is not allowed on Windows. Yeah. Windows implements bools very differently, apparently. I mean, it shouldn't be allowed anywhere, but this implementation, this the correct implementation. Anyway, okay. So the first thing we do is call .b32. No, actually, let's do a absolute call. So move absq $0 into $rax call star %rax. So this is the address of main. Also, this needs to be at the top. x86c libc begin, and this will be global x86c underscore libc underscore begin. So we'll enclose everything inside this. Yeah, and now we do sysexit. So rax contains the return value. How do we do sysexit? Sequence of instruction. It's fine. Syscall exit takes the status in RDI, RSI. What is it? RDI, right? Yeah, RDI. So move q rax into RDI. What is the syscall number for exit? Sequence of instructions for syscall. And on sysv, everything is using a 64-bit registers, right? I mean, I think so. Actually, no. If you pass in, eventually, I mean, it uses 64-bit registers, but it does truncate values. I mean, it doesn't do default promotion. Like if your function expects a 32-bit value, and if you pass a 16-bit value, it only promotes up to 32. I think, not exactly sure. It's been a while. Okay, so RX is 60 and RDI is. Okay, so this will do our syscall at the exit, and then we need to compute the size. So we say x86c libc size. The problem is the size won't be. We need to do x86c libc end. Okay, so we have our two labels now. I could just put it into this some data section too. Yeah, that's better. x86c libc size dot quad x86c libc n minus x86c libc underscore begin. Actually, I should probably use special names for this libc and then begin. Okay, so now we have the size, we have the start and end. This just needs to be similarly copied into it. So we first execution area prepare. Okay, so this copied over the headers. Now we need to copy over the no, first this. Where's the start? Here, start. No, this is size. This is the start. So this gets R14. So the start of the libc start goes into this now because the very first function is start. So it has to go into start. That's correct. I'm going to put a comment here. x86c libc start has to be the first function. Okay, so this is fine. We have copied over, we have written it down. Now we need to also copy over the libc x86c begin. Okay, RIP into RSI and move Q underscore x86c libc size of RIP into RCX. And then you can do the same thing. Rep move SB, right? Yeah, so this will copy over the libc2. And then we finally do, yeah, this is fine. Now the only thing that needs to change is in our table, in the global symbol table, we always put the old address of putchar, right? This was in parser, yeah. This one now needs to change. This is going to be x begin plus code gen buffer. Is that correct? No, it's not. It's not x86 libc code gen begin and code gen buffer. This is fine. Plus ELF header size, right? Is it ELF header size? But we don't have that here. Okay, let's think. So, how do I compute the address of putchar? Needs to be patched. I don't want to patch it in post because it will be used in a bunch of places. So the problem here is we have the libc x86c putchar functions addressed. It needs to be adjusted. to be in the code gen buffer, not in the libc section. So this will give us the address. This will give us the like where does the putchar start in libc section. We somehow need to add code gen buffer plus elf header size to it. And I guess I'll just use a constant. (64 plus 56). Fine. So this becomes elf header size, right? So we have x86 libc putchar minus x86c libc begin. This gives us the offset within the libc of putchar. Then you add codegen buffer to it so that it goes to the start of that, and then you add elf header size to it. Okay, perfect. So this way we have the right addresses. I mean, ideally I would have liked to put the like the implementation of this libc itself into the codegen area. The problem is the flags. Like I need to have this correctly, I need like to have bits, which means that the data needs to be loaded from the executable. But the rest of the bytes in the codegen area, I want them to be uninitialized. I don't want them to be loaded. So that's why I'm using BSS. Now it's surprisingly annoying to like get them lined up properly. It's just better if I copy it over. I think this should take care of it. Oh wait. So also this is complaining. 508. Yeah. What is this saying? Invalid operands, undefined and undefined section for minus. Am I not? Is this not allowed? Wait, this should be fine, right? Cannot resolve x86c libc begin. Huh. What about this? This was okay. Okay, that's different. Let's x86c libc begin. Libc begin. Did I not export it? I did not. Underscore x86c libc begin. Underscore x86c libc begin. Wait, this is correct. Why can't it resolve it? Is it because it starts with underscore? That shouldn't be a problem. Wait, do I have to manually fill this table in? I don't want to have to programmatically fill it in. Yeah, turns out you can't do this. Can I store the difference of two labels in a quad in the data section? Would it difference in the address and the difference in address? Can the actual labels be in different translation unit? God has to take from different translation units object files at assembly time. Okay. Linker relocations. Why can't I do difference? How do I get difference across files? Calculate at runtime. Fine, we'll do it at runtime then. So patch in address of x86c libc put char. This is annoying. Put underscore char. So global symbol table, we'll have to just do this manually. Let's go to prepare execution area. So we did the headers and everything. Copied over the libc. Now we need to patch the global address. Okay. x86c libc put char of RIP minus into RAX subq rx rx. So rx equals to rx minus rx, and then we do add q. No. I don't like how this has to be done. We could do two separate sections and then load them in the executable. That could also work, but yeah, it's fine. Let's just copy it over. Let's keep it simple. Cogent buffer into rbx, add q rbx into rax, and then move q rax into 8, is it? Yeah, global symbol table of 8. Okay, so dispatches the address of put char into the in the correct place in the symbol table. Okay, now one final thing. In the finalize, we forgot to put the address of main. So this actually goes somewhere else. Let's actually make this up. relocation against ELF header size cannot be used when used. Oh yeah, I forgot to add ELF header size. Okay, now ELF header size also needs to be added. Okay, and finally obj dump dash s build x86c libc.o, and we need to find the address of this, which is just literally 2 bytes into start. Needs to be patched, but the complex math needs to be done. So this is cogent buffer plus size plus 2. Okay. Cogent buffer aq cogent buffer of percent RIP into RBX. Cogent buffer. Now move Q RAX into ELF header size plus 2 of RBX, because you have the headers and then you have the libc, and 2 bytes into it is literally our address of main. So this works. Now let's see if everything works. Okay, of course. Let's do read elf dash a empty. So the address now is 5D7B19C44000. It seems wrong, because the virtual address, it's somehow back. Oh, I think I did some address calculation wrong. Yeah, the entry point address is wrong. Okay. Yeah, this one is wrong. So no, this is size. This is the entry point. This one. ELF template header entry minus ELF template header entry. Yeah, this just seems wrong. Yeah, how is this even compiling? Okay, let's do the math correctly. You know, I think the only thing missing here. Okay, so ELF template header e entry minus ELF template header plus cogent buffer of RIP. It wrote R14 there. R14 is the end of header. This seems fine. The start of the program is entry point address. Yeah, and that's what I write the. Let's just put a break on prepare execution area and see what goes wrong. Execution area. Oh God, I cannot go through this. Can I do until? Okay, thank God. How the hell is it 8,000? Oh, because I did not move it into R14 yet. This should be RDI. Okay, we'll do it. Okay, finally, something ran correctly. And we got 25. Is that what we're supposed to get from empty? $13 plus 12. Yes, we're supposed to get 20. Okay, now let's check rest of the programs. Let's do Fibonacci. Examples, Fibonacci, Fib 30, yes. Let's do factorial. $120, perfect. So our ELF executables are running correctly. And the good thing about this is now we can run this as many times as we want without having to compile them again. And we can also debug through this much more quickly by doing this. It doesn't have names because we don't have symbols, but we have our whole function here. So we can do si. This goes to our main function, and then we have a bunch of stuff in it that does the factorial computation. But this is good. It looks at other examples that we have. We have precedence, short circuit. Let's do precedence. $63. Was it? This is what's supposed to print. Yeah, I think this is correct. 55 plus 8. Great. So we have our ELF executable working correctly, and we also have our libc functions patched in properly. This took a long time, but it finally worked. So I'm actually confused as to why I can do subtraction here, but I can't do it in a quad. I can write the difference of two labels. In a memory operand, even when they are not in the same file. But I cannot do that for .quad. When you use memory operand in the instructions like this minus this RX, you aren't actually doing what you're thinking. What? And you cannot use the difference of two external labels in memory operand either. Here's the difference in instruction. If you try to write in this and this will fail if the labels are external. I'm gonna give it an example. For example, I can successfully assemble this where ELF template header e entry and ELF template header are in a different file. Wait, are they in a different file? They're not. Oops. This was silly. Now it's just making up. Gemini is just making up reasons now. Amazing. This is so stupid. Because ELF template entry and ELF template header are in the same external file. What does same external file mean? And presumably, I mean, yes, a different section file, and in the same section, the assembler can calculate the distance before it even talks to the linker. But how can the assembler even look at the other file? The other file doesn't exist. It's just making up stupid stuff. The assembler still seems. Yeah, I guess this is just working because it's in the same. It's in the same section. All right, we have everything working, friends. Should test this. I'm actually going to write some test cases for this and make sure that everything runs. Start by doing one by one. mkdir-p scratch, or you can do build/scratch. This depends on all. Okay, we're going to do just compile all the executables. So we do build. Why am I doing this? This needs to be build dir. The executable name, right? Executable name. exdir equals base dir examples. Exdir, comma. Which ones do I want to compile? I need empty to build dir, comma, scratch, comma, empty. I mean, I could technically write this properly as code like by rules, wildcards and stuff. Yeah, let's do that. Examples equals wildcard $source dir, star.c. Example executables equals substitute exdir, comma, build dir, comma, examples Let me just do this properly. Comma, examples, colon dot c equals nothing. Okay. Now, test depends on example executables. Now we need to write build dir person examples colon percent depends on exdir colon examples, just exdir colon percent dot c, and executable name. And then the way we compile this is executable name of $is -o $at. Okay, make test. Great, all our executables are compiled, right? We need to start making things precious. Actually, somehow this doesn't need precious for some reason. Oh, I don't know. Precious build dir colon person dot o precious. Yeah, I'm confused. Why does it delete those? Wait, what is this syntax even? Oh. God, how do I delete this file? In bash, how do I delete file that starts with dash? Okay, this was the issue. It's like, what is even happening? Wait a second. The less than is going to okay, yeah. This doesn't really need precious. When does it need precious? If it's created by rules, yeah. Okay, this is fine. I'm just gonna remove this. Okay, so all our executables are running. I should still just execute them for exec in executable names, no, example executables, do sample exec. Done. Right? Some ran, some did not run. Echo $$ exec. Why does while loop fail? Oh, it's just the output needs to be ignored. Okay. I don't like how it prints the whole name of this in some numbers. Okay. Great. Now we have all our outputs printed correctly. Let's put kya do? Print hello world. Okay. So we have our test cases written down too. Great. Makefile, source def, source driver, source execution area, source parser, source tokenizer, source x86 libc. Get working ELF generation and excuses. What time is it? It's 4:30. We have time another 1 hour. What can I implement in 1 hour? I do want to do operators. So let's do address of operator and dereference operator so we can do pointer arithmetic. Okay. So what? No, this should be in parse expression. Yeah, so remember how we had said the unary operators on the left go here. So these are a little tricky because we might have them nested and they need to be handled one by one. So one way to do this is if we do see an operator, we remember that and then recursively call the same function with the same priority, with the same precedence. Um, and then on the way out, we handle that operator and continue. Yeah, that will do that. So we first check for a we also have to change the precedence of the assignment, but we'll do that later. So the algorithm for this is if we see a unary operator, we parse the next statement. Yeah, so if we see a unary operator like ampersand, we parse the next statement with the same precedence again, but recursively. And on the way back, we implement the operator. There's a couple of instructions we can, I mean, there's really not much, but size of we cannot implement because size of is a special operator. It works on type of the expression, so it's not really, yeah, we'll need a separate way of determining size of, so we'll have to implement that differently. But let's say star ampersand plus minus not, these can all be implemented correctly. So let's start with ampersand and star. Okay, let's do this. So call get token. Actually, we already did that. Compare queue. Let's implement just token ampersand. So if it is a token ampersand, we move Rx to save. Right, and then we call parse expr pre again. So if there is a separate operator, yeah, so at this point the expression would be parsed and the value would be at the top, and then we implement the operator. However, this should only be checked for precedence. Yeah, this is only being checked for two or low. Yeah. So it's only being checked for two or low. It won't be checked for everything along the way. Does it matter if it's checked? Yeah, it does matter, because if you have ampersand, yeah, okay, and these have right to left precedence. That's right, because yeah, we'll handle it recursively. Okay, I mean, honestly, this could just be moved out into a separate function for 2, which is just like handling all of this, but it's fine, we can just continue anyway. So yeah, I mean, we could just do this as a separate function. this came from integer expression global, yeah. Okay. If it's not jump on not equal, oh, but this will break the, yeah, so what will happen is 2 and then there's 1. Right, so these function calls are the highest precedence, which means that needs to associate first before these associate. Okay, so we have to separate it out. That can only be, so the closing parentheses can only be handled in 1. Right. Yeah. Yep. So this has to be handled separately. Special case this, it's fine. Let's remove this for now. Basically, I'll give an example of what happens, what would be wrong. If I have a function like this, right? If I do it the way I'm suggesting right now, like where I check for ampersands immediately, this will take address of foo and then call function on it. Whereas this should actually be parsed as function call first and then address of. And this might not matter for address of because invalid, but like this would be a problem. If I try to dereference the return value, this would try to dereference the function and then do the star. Whereas this should be actually this. And to handle this, we have to do the precedence correctly, which means 2 and 1 need to be handled separately. So basically we need to, like, just like we had this, we just make parse expr pre 2, parse expr pre 1, and parse expr pre 0, right? This will just name it. Okay, and so in parse expr pre, we just some things need to be moved around. So it says compare if it's 2, if it's equal, let's leave this for now, jump on equal parse expr pre underscore 2. And 1 and 0 doesn't need to be handled here because that will be handled as part of 1, like the 1 can only be called from 2, so we don't need to handle it. Okay. This will only call here, so we can remove these, but 1 second before we remove this, let's start moving things around. Okay, so in 0 we do this. 0 says zero is identifier or integers. Parse expr pre 0 continue. Parse expr continue. Parse expr pre-0 continue. This function call also needs to actually go back to pre1 continue. Okay. Parse expression pre-0 continue. Then what does this do? I guess this can just do leave and red, right? Yeah, so we parse the integer. No, it needs to generate code. Yeah, the generation will happen there, and this will just leave red. Okay. The token has already been popped. Needs to go here because we're jumping right before. Okay. So pre-0 is stop. There's nothing else here. It just checks the expression. It has to either be an integer or it has to be an identifier. There's nothing. Okay, then 1. 1 is function call. So what this will first do is call parse exp pre-0. This, yeah, for it to be 1, it has to be a 0. And now we check call get token, compare token L parent rax, jump on equal. We already have the code for it. Parse function call expression. Yeah. If it's not, we just simply do leave red queue. Oh, hold on. We can't really call these directly. Actually, yeah, the stack frame setup needs to be copied too. Actually, no, we don't need stack frame setup for this. This just needs to be without leave. This is fine. So this just moves here. Okay, this will handle all the main cases. Finish. Yeah, it does do the right thing. So this is not required either. Pre-continue is not required, right? Yeah. Okay, I'm simplifying a lot of stuff. So this is only handling the binary operator now. Yeah. We'll move stuff around to be close by, so we don't have to jump around too much. Okay, so one is just, right, so it calls pre-0 first, then it calls get token. If it is lparen rax, then it jumps to parse function call expression, otherwise it call return token, right? We can't, yeah, that if it's not a parentheses, it needs to be returned, and then go back. But we don't need leave for this. Yeah, this is good enough. And for parse 2 is all the unary operators. So this actually needs to call expression 1. No, needs to. What needs to happen is there might be multiple of those, right? Like it's not just one. Like there could be more of those. So yeah, parse the function call expression, and then we have parse exper pre1 continue, which is where the function will perform. Then we'll jump to parse exper pre0, no, pre1 next, yeah, which is here. Parse exper pre1 next. Yeah, so this will keep on checking if the there's like lparen on the right hand side, and if it is there, it will keep on like calling the function, because what we might have is something like this, and this requires us to also call the function on the return value. So we need to keep on checking the right hand side, which this will handle correctly. And now finally pre2. Now pre2, we cannot do it as like a loop. It has to be done recursively. This is the part where we do it differently. Wait. Yeah, it's a unary operator. It doesn't need a second expression. But when we call 2 finally, what's handled for 2? Call, and yeah, and at the end, when one of them, it won't be lparen, it will return the token and then exit. Wait, what? No, just be sure. Yeah. So if it's not an rparen, it will return. Yeah. And while it is lparen, it will continue. So if I'm just gonna do this anyway, might as well put this here. Right. Great. No, this seems wrong. Okay, so if it is a function call, we jump to the function call. When that returns, we go to the next one. Perfect. Eventually, it won't be a function call, which then we'll return from. Okay, the parse expression 2 needs to get token first. We'll say call get token. we need to check if it's ampersand. So compare q dollar token underscore ampersand rx. Jump on not jump on not equal parse expert to not amp. Yeah, this is annoying. Parse expert to not amp. This will handle the next operator type, but for now it's fine. And now here we handle the ampersand. So we have already consumed the ampersand. So now we call get token, no, not get token, we call parse expert to again. This will eventually reach to a point where it won't see anything. But on the way out, we need to generate code for it. And finally, this will do call q parse expert pre1 and then return. So this will basically, yeah, handle all the unary operators. Now, we need to generate code for ampersand. So we already have the address on the stack. We just need to pop a couple of things and push one out. So let's see. So generally we would just do, this is amp pop q rax. This gives us the address. Pop q rbx gives us the value. Push q rax. No. Yeah, we'll put the address as value and then push q0. Null pointer, which you can call whatever. Control R GCC, control R obj dump. So it's just these 5 instructions. So the problem right now is we don't have pointer types. But if I just use integer, I think it will be fine. We can test this. If I add the ampersand and star operators, I think this should be fine. Okay, so this does not amp. Yeah, this is fine. And now let's do the dereference operator too. But before we do that, we need to call return token. Because when we go to parse pre1, yeah, this token, if it's not ampersand, the token needs to be returned. But it should not be returned on rest of the ones. this actually needs to return. Yeah, it needs to keep on recursively calling, but as soon as it recursively calls, it cannot look at any more tokens. Yeah, that would be wrong. So we just return from there. This is fine. Not amp. Compare q dollar token star percent RAX. Jump on not equal parse expr pre to not star. Yeah, so it's not star, not amp, so it's fine. Now if it is star, same thing again of generating. Yeah, if it is star, we go back to calling it recursively, and then we need to generate the instructions for star, which is just the reverse of this. So we do popq rax, this gives us the address. We do popq rax, which gives us the value. Then we do pushq rax, and then pushq. Yep. So address goes away, gets value, puts the value, and then puts the address back. Yeah. Of course, it's 5 bytes again. Okay, so if it's not ampersand, not star, we return the token and go and parse the next higher precedence. Perfect. This is good. Now let's test this out. First of all, does this even compile? Nope. 75. And that does compile. Okay. The test seems to be fine. I should write the reference down somewhere, reference output down somewhere. Okay, but this seems okay. So this is working correctly. Now we just need to write a pointer example. Pointers.c. Let's make a local variable, int x equals to 5. Now I'm just going to use int, but this should not be int. It should be a actual address. So equals ampersand x. So we'll store the address of x in y, and we'll say star y equals to 45, and then we'll say return x. So this should return 45, not not 5, and it did return 5. So that's wrong, right? technically this is a type violation, but let's just step through the code and see what we get. Good thing is now we can directly step through the generated code instead of having to attach it to the debugger itself. Actually, we can first do obj dump s build examples pointers. Unfortunately, that section is not named. Isn't that like B? What is the section? It doesn't have sections. Okay, fine, I'll just do GDB. Okay, so this is start function. This is the main function. Push 5 takes 5, pushes into -8 RBP, which is correct. Then loads the address of RBP and RAX into RAX, pushes RAX. This is the address, this is the value. Then pops RAX, which gets the address. Then pops RBX to give the value. Then pushes the value, pushes it as value. The address is value. We should check here what it is after this /x $rax. It is the address of that variable. Let's see what the value is at this address. It's 5. Okay, that's great. So now the address got stored into %-1. This loads it. This loads the address of the register. This. Oh no. What? Why did it finish? Okay, this one loads the value of, yeah, so at this point it should still be the address of that variable. It's perfect. Okay. Wait, where is that 45 equals 45? Huh? The code was never generated for it. *y equals 45. This itself is wrong. Wait, where is the 45 quotient? There should be something like 245, right? *y equals 45. That should load the address of y into, load the address of x into register and then store 45 there. I don't think I ever got 45. 45 is, yeah, this seems weird. Do we see the constant 45 anywhere? I do not see the constant 45 anywhere. Yeah, okay, this is definitely wrong then. So what happened here? What even happened to that? Wait, did I consume an excess token in star? Parse integer expression. Yeah, this literally just parses one integer and goes to parse exper pre-0 continue. It just returns. There's nothing wrong. Oh, but if it's not, no, it has to be one of them, right? Once it reaches 0, it has to be one of them. Let's put an error message. Invalid expression. Invalid pre-0 expression. Okay, this was wrong. Okay, we have a starting point. Wow, this is really like, there's a bunch of operator calls on. Actually, this is wrong. This is not, stack frame is not set up properly, so it just gives a bunch of wrong things. But this is what we want. Frame 1. No, we need to put a breakpoint on pre-0. It is 2, so this should not fail. Continue. This is 1, so this is identifier, should not fail. One, also identifier, should not fail. 3D for some reason. What is 3D? Equals. So it got an equals when it expected an integer or right. Why didn't it get called? Okay, so this must have happened here, right? This is the only place this can happen. Star y equals to 45. It's interesting. Star y equals to 545 seems wrong. Why is it consuming? So the only place precedence 0 gets called is from precedence 1. Like this is the only place where it can be called, which is precedence 1 is these kind of function call expressions. Okay, this is fine. And this must be called from pre 2, which is here. Okay, let me check if this works. This works fine. Okay. And let's try to do this to make sure it works correctly. Okay, so this works, it's just the star is not working. Fine, this is easy to figure out. So when we get into parse expression not to, we call get token, we check if it is ampersand. If it's not ampersand, we go to check if it's star. If it's not star, then we call, oh yes, here's the problem, we didn't add ret q here. Once it matches a star, it should not try to go to R1. Yeah, that was the issue. Where did 120 come from? Wait, insane. Oh, it's y. Sorry, there should be x. And it's 45. Perfect. So somehow our pointer arithmetic is also working correctly. Should probably implement pointer types to do this correctly instead of having to do this in integer values. It's fine. We just have to like change parse type to also look for pointers afterwards, right? So here we check for all these. If it's one of them, and then we just say call get token compare q token star %rax jump on equal parse type done, otherwise call return token. Yeah, so what this will simply do is it will consume all the stars that appear after that int. Um, this should be fine for now. So let's change this to and our pointers return 45, so that's great. This is also because we don't have type checking. Like previously we should have complained, the type should have had like an error message. So what needs to actually happen now is in parse type we need to somehow like incorporate this into the type. So you see how this just like returns here in RAX for the type is, then we move it into R11. We need to somehow encode that, hey, this is not actually just an integer, this is a pointer to an integer. It'll be relevant later when we do type checking, but for now it's okay. We just doing. And now that we have ampersand and star working, we could also actually implement putchar ourselves by just giving a syscall function. That's fine. We can do basic. This is fine. I think this is a good point to stop. We are 7 hours 15 minutes into the stream. Do folks have any questions about specific parts of what we did? Long stream, yeah. It's I usually do this. So I mean, if you're new here, if you haven't seen these before, this is where I post them, by the way. So if you go to this website, I mean my YouTube page, there is a playlist here. There is a playlist here where constant I have the previous ones done too. Feel free to watch these. I'll post today's right away after this. But if you notice, all of these streams, like they're both 7 hours, 30 minutes. Today's will be another 7 hours, 15 minutes. Awesome stuff. Inspires me to work on my toy lang. Hey, yeah, please. Oh yeah, I was gonna take a look at your toy lang. I'm just gonna close this first. Let's see, share a GitHub link here. Tiny embeddable statically typed programming language inspired by C and Python targeting WebAssembly. Super cool. Oh, that was WebAssembly then. I guess it's similar to ARM. I'm not sure. Motivation, we'll need to set example 12 Fibonacci number. Yep, that's exactly how we wrote it. But we're just writing C. So on C side, we initialize the C. Sith runtime provide an implementation of print and so it's a embedded Python in C basically, right? So you have Sith init, set function. Where does print come from? Oh, it's here. Interesting. Oh, this is basically saying, this is giving an implementation of print. std print.void. Okay. Interesting. Sith generate takes JIT, and I guess Sith init takes the name of the file, I'm guessing. Yeah. Super cool. You're building like a runtime around it too. With a few lines of code, Sith can call into C and C can call into Sith. Try the playground. Oh, you have a playground for it. Here. Nice. So this is a whole Python program. And I guess you don't need the C one because there's like a default C one, C code that calls this. Oh, nice. You have a whole rendering thing going on. I'm guessing. Oh, yeah. Okay. It's a snake game. Super cool, man. If I was good at this. Nice. And so stuff like draw. No, draw is just implemented here, but then rect is implemented here. Okay, so you have in environment you have variables declared, and I guess where do I see the C code for this? The playground uses Wasm backend. That's pretty cool. Yeah, I mean, it would have been nice if I'm not good at Wasm. But I want to see where the calling C code is. Can I not see that here? I guess that must be fixed for this Wasm runtime because someone needs to provide those implementations. You have sphere. Nice. This must have taken a long time to implement. Wait, it's actually doing occlusion. Pretty cool. Ray tracer, a complete ray tracer. Nice. This is short out, man. This is amazing. Press S on the sphere example. Yes, nice. Shades it too. So it is a full ray traced version. Pretty cool. Prospero. What does Prospero do? Nice. Fibonacci, Mandelbrot, falling sands. Nice. And this uses map. No, map is here. So it must eventually use rect. Okay, rect and fill. Falling sands. I'm guessing I'm supposed to click somewhere. Okay, yeah. Nice. This is so cool. I mean, I'll have to look at how you implemented. This is my first graphics program, so I ported it. I see. Yeah, I mean that's the whole point, right? If you can port existing code bases, that means your language is rich enough instead of having to write everything from scratch. I mean, that's my eventual goal. I want to get this basic compiler working and then take an existing off-the-shelf compiler like say Tiny C or something, and then get it to the point where I can compile this with my ASM compiler. So that way I don't have to write a full C compiler from scratch. Like this is a standard compiler, standard compliant compiler. I think at least to some reasonable extent, more than ours. There are some backend is less exciting than JIT backend, but still cool. Yeah. I'm rewriting the entire API right now, so if the functions look weird, then it'll be fixed. No, I mean, I trust you. This looks very polished and great. Is there somewhere like we can follow you? Do you have like a Twitter or something you want to share? I'm happy to post it here. This probably needs to stop. It's taking up CPU. But yeah, this is amazing. Give a star on GitHub. Yeah, that's what I'll do. I was just looking it up. Oh, I need to log in. 1 second. Yeah, I'll keep following it. This is great. Yeah, and our what I'm working on also is being shared here. So if you go to this GitHub, this is what we are working on. I need to write some readmes and I need to write some stuff. Yeah, thanks for looking at it. Of course, thanks for sharing. This is really cool. It's always good to look at other compiler projects, learn from them. Yeah, this is a different kind of compiler, right? Like this is the focus of it. It's a assembly 97.5 and then 2.5% makefile. There's no like, yeah, the fun part is in this. I'm having fun with it. I think this is, yeah. We'll continue next week again, next Saturday. Next Saturday, I'll try to fix, so we have fixed up a lot of issues now. We don't have to worry about precedence. The next thing I'm planning to do actually is improve the code generation. So right now, if you notice, everything is done through the stack. Like sub-expressions are evaluated, results are pushed on the stack, the next sub-expression pops it off. I think that's extremely slow and like unnecessary. It's hard to read too. So what I'm gonna do is actually use intermediate stack slots. So all intermediates will actually go onto the stack and then be read from there. So we don't have to keep pushing and popping. Furthermore, I'll also try to optimize like not all intermediates go into the stack. Like for example, if you have two operations A and B, like A plus B, A will have to go into the stack, but B itself can be in register and it can be chained into the next sort of operations. That way we can like simplify code generation quite a lot. It'll make reading code much easier. So I'll do that next. And then after that, I want to get rid of like the tokenizer spacing thing. Like right now, if you notice, our tokenizer is so simple because it requires the users to put space between tokens. I'll simplify that. And it's actually pretty straightforward. What it basically does is like, once you enter a type of like token, like you say, oh, okay, I'm passing an identifier, you currently we just stop at space. It will eventually like stop at, if it's not the same kind, I can stop. Is this all planned to be single pass as well? It is. I made this decision pretty early on where I thought about it like, should I generate an intermediate and then generate code from the intermediate? The goal is not to do optimizations. I couldn't justify implementing a whole intermediate in ASM to do that. So I decided to stick with the parser and code generator intertwined. It's not even a single pass, it's like a zero pass execution, right? Like the code generator and the parser are fused together. It's not great, but I think it's the spirit of it is that it's a bootstrapping compiler. We want to get a working compiler that can then be used to implement a full-fledged compiler. So yeah, it'll probably stay like this for now. I mean, if I had made an IR, it would have been so much better to do this thing I was struggling with today, like the precedence for short circuiting would have been so much easier to implement because I could just look ahead and see what the next expression is. But right now I can't do that, so I have to like do this ahead of time. Are you using tries for lexing? No, not really. For lexing, what we have simply done is we've actually made the lexer very easy, which is you start from the token, you check which type of a token it is, like if it's a special character, if it's 0 to 9, if it's like a identifier and so on. And what we basically do is we make the tokens themselves by taking the bytes of the token. Like for example, like if you have I and T, right? We literally put the bytes of I and T into a register, and that is our token. And because all our keywords fit into 8 bytes, we can just keep it in register. For identifiers, what we are doing is we are putting the identifier into an identifier table and putting the index into the identifier table into RBX. So that makes it actually very easy to create. Yeah, so we have like keywords defined in def, which is here. So you'll notice that our keyword char is just this constant, keyword continue is just this constant, and so on. That makes like tokenizing very easy. And one simplification we did is like every token needs to end with space. So once we figure out which type it is, we just read till end. What this does is as long as we don't see a space, we're going to keep reading. And at the end, whatever number of spaces there are, we consume them. So that way it's easy to lex. And this works. I'll make this more complicated later. I will like implement cases where we can stop at the right token, like the right character. But I wanted to get something working, so I did it this way. This is also inspired from one of the projects that I was looking at earlier, which is Sector C. It's an amazing project. Learned a lot from this, which is basically a 512 byte ASM compiler that sits in the boot sector of your disk. So you can literally boot into a compiler. It's actually extremely cool. So a lot of like these ideas were borrowed from that. So including like tokens can be made by just putting the numbers. They do a hash of it. I just literally put them into the register. And then other stuff like the spacing and stuff, I think I learned from them, except for like they still handle stuff a little bit more. Like they handle semicolon. I don't. Like I just say space everywhere, but eventually I'll handle it. Yeah. But it makes a lot of things easier. So the tokenizer is actually very easy. You'll say just like 200 lines of assembly, including like data and stuff, including like these definitions and stuff. The parser is now getting more complicated. It's 533 lines, but it's not a lot. Like this is parser and code. Sorry, this is just parser, and then we have parse expressions around another 500 lines. So it's like 1,000 lines assembly of code generator and parser integrated together. I think that's reasonable. And then we have like the driver code, which is another 100 lines of code. So it's not a lot. Anyway, what did I change? New. I'll just commit these changes. Parse expression, source parser, example pointers. Need to head out. I'm gonna head out too. Thanks for joining, and hope to see you next week again. Alright, see you folks. I'll post these videos on YouTube immediately after this. Thanks for joining.